The shear stress between two adjacent layers of a fluid is directly proportional to the what? Now you can see that that thing is called a law, and is the law of what? Viscosity. Newton's law of viscosity. It states that what? That the shear stress is directly proportional to what? If you want to say the layman, shear stress is directly proportional to what? Velocity gradient. But we know that this thing now, this law is governing the radar of fluids, right? So that's why we want to now incorporate terminologies like adjacent layer, fluid, and the fact that it's going to affect the rate of change of velocity with distance, which is the gradient. So you state it properly. The Newton's law of viscosity states that the shear stress between two adjacent layers of a fluid is directly proportional to the what? To the velocity gradient. It's directly proportional to the velocity gradient. All right. So that's that for that. Dynamic and kinematic viscosities. So if you look at this dynamic viscosity, and we have kinematic viscosity. The dynamic viscosity also called the absolute viscosity. It is the proportionality constant in the law of viscosity. Listen, that's the particular viscosity that, you see, that's the particular viscosity that causes that resistance whenever you are trying to stir a viscous liquid. You understand? It makes stirring difficult. Whenever you're trying to stir a viscous liquid, yeah. But when you want to turn the liquid from one container to another container, you start feeling that stress, that you start feeling that difficulty. Especially when it's something like honey or something more greasy, stuff like that, you feel that more of reluctance, right? At that point in time, what's playing is kinematic viscosity. You see, but which one is the absolute viscosity? Which one do we call the absolute viscosity? The dynamic viscosity. Did you get that? All right. So this is the relation between them. Yeah. It's from here you get it. The kinematic viscosity is equal to dynamic viscosity over density. Next slide. Shear stress in the fluid. So the shear stress in the fluid, you can see, it acts how? Parallel to the surface and opposes relative motion between layers. So it's the shear stress that is actually making the fluid find it difficult to just flow freely through a pipe. I get you now? Because he himself acts parallel to the walls of those pipes. I get you now? So every single, that's why eventually all fluids, especially for fluids that have viscosity, because when they flow through a pipe, like something like this, when they flow through a pipe and something like this, you see that this is how their appearance will look like. You know why? Because those ones, the components, the molecules of the fluid that are closer to the wall, they are experiencing some level of extra resistance. That's why you see them here at the back. And those ones more at the central point, you see them more at the front. That's the shear stress effect on this place. I get what I'm saying now. So that's it. That's it. Which one is absent? If the shear stress is absent, there will still be, it's not a complete good thing. Yes, flow will be fast, but when flow is fast, it gives a tendency to what? To turbulent flow. A high velocity flow has higher tendency of becoming a turbulent flow. You understand what I'm saying? You know what turbulent flow are? Okay. When you're having those, very good, those irregular circular, what do you call it? Displacements from the normal straight part of the motion, maybe due to collision with obstacles. You have these things. So shear stress is the tensile force per unit area exerted by the layer of fluid adjacent something. You said that. All right, next slide. Velocity gradient. We said whenever you hear about gradient, we're talking about what? We're talking about something over length. So velocity gradient is the rate of change of velocity with respect to distance, normal to the direction of flow. So velocity profile in laminar flow. You see? Umax. You see nothing I explained here. Did you see what I just explained? You notice that these ones that are more at the center are faster than those here. What's causing the resistance of the walls to the flow? Even in the blood vessels, it happens. It happens. That's what they explain as compliance and resistance in blood vessels. So when blood vessels are constricting, it causes resistance to blood flow. That's same thing as seeing in velocity gradient here, how it causes this resistance to blood flow. All right. Yep. Okay, hold on, go back. So here now is the same thing as the velocity gradient, hope you know. Change in velocity over change in R. So we are taking a smaller fragment of the length, and that's why we're calling it R, right? You see that that is still equal to 2U max over. So I'm trying to say that that rate does not change. That gradient is kept constant across the motion of this. The big R, look at it. The small R is here, the big R is here. Do you understand? Okay, what they are trying to do is take a small fraction, imagine a small fraction here across this full diameter of this stuff. Take a small fraction. They call that small fraction du. As you're taking a small fraction of that, you're taking that means you're studying a small fraction of the velocity. So that means you're calling that one du. So having the du, I'm having a small fraction of the distance you want to study, dr. And we are trying to say that the event that happened when you are studying the du dr is what will happen eventually as the major thing you see now. So that's what they generalize. But what is the cause of the minus? Because of the fact that these things are near wall events. They will cause what? Look at R now. You know R and this one, they are the. So it will cause those drops. It will cause those drops in velocity. Where R is equals to radial distance from the center. All right, yeps. Let's go. So we have this again, Poiseuille's equation. So the Poiseuille's equation is a very important poem. It's a very important equation for fluid. It's a very important equation for fluid. So it gives the volume flow rate of the viscous fluid through a long, straight, circular pipe under laminar flow. Are we there? So what is this? The flow rate, right? And then you have pi R4, the change in pressure divided by 8 pi 8 mu L. Are we together here now? 8 mu L. So that's it. Gives the volume flow rate of viscous fluid through a long, straight, circular pipe. That's it. So what are the important implications? We're seeing now that flow rate highly depends on who the most. Radius. The next slide is ready. The next slide is ready. Important implications. G equals to, the R4 depends more on who? sorry, the Q depends more on the R4, that's on the radius. Why? You can see it depends on it in the fourth order of dependence. That's massive. I mean, a small change in R can cause a massive change in the value of the flow rate. Yes. So we also see that pressure difference affect flow rate, right? They are proportional. The higher the pressure difference, the higher the flow rate. But you see the inverse relationship there. You have the length and the viscosity. All right. Yeah. Yes, next slide. Okay, this is it. Sorry. Flow through a capillary tube, right? Capillary tubes are very small tubes of circular cross-section, radius usually less than 1 millimeter. That's actually really, really small. The flow is always laminar. Capillary constant, we call it K. So K is equals to pi R4 over that. So thus, say Q is equals to K this. So that means the whole of this thing here is called capillary constant. It's a very, very important thing to know. Very important thing to know. What are the uses? Measurement of viscosity, blood flow in small vessels, and microfluidic applications. Example of a microfluidic applications is what? The vessel of tearing, the eye. You understand? And some other smaller vessels. All right. All right. Next slide. Stokes' law, very beautiful. So, you see, Stokes' law is that law you don't want to joke with. Yes. The viscosity drag force on a small sphere moving with steady velocity through a viscous fluid at low Reynolds number is given by Stokes' law. Now, this is the expression. What am I trying to say? This Stokes' law is only valid when the flow is steady, the fluid is incompressible, the sphere is small, and Reynolds number is less than 1. Yeah. So we have applications, sedimentation of particles, falling raindrops, and then motion of microscopic particles in fluids. That's part of places that you actually apply those concepts. So you have a small spherical ball, and then you drop it into a viscous fluid. You want to study the force, the drag force within there. So that's the expression that you use to study it. All right, but terminal velocity is the constant maximum velocity attained by a body. So you see, when the body is falling through a viscous fluid, initially there will be a point where you attain a velocity that is steady and continuous. That means the word steady and constant. Are we together here now? Steady and constant. So yeah, steady and constant. So condition at terminal velocity is that the weight should be equal to the buoyant force plus the what? Drag force. The weight, because the weight now is the only one acting downwards. Buoyant force is acting upwards, drag force is also acting upwards, and they must balance out. So you can see the formula for the drag force, which we saw earlier on, is Stokes' law. And this is the buoyant force, which we've done already earlier on, rho GV, right? So solving for terminal velocity is to make the V subject of the formula. Yeah, that does it. Making the V the subject of the formula. That gives you the terminal velocity. Let's even do that. Right? So drag force on the sphere. That's literally what we spoke about earlier on. It's just that for when the Reynolds number is higher. You know, this one is when the Reynolds number is low, less than 1. But when the Reynolds number is higher, we make use of that. We make use of that. So take note of it. I believe this one looks familiar to you already. What was it? The normal jet force. All right. But this one here now is the drag coefficient. Let's move on. Laminar and turbulent flow. Laminar and turbulent flow. So when you hear the word laminar flow, when you hear the word laminar flow, what does it mean? You can see that they are steady, parallel to each other, and they are more streamlined, right? They're more streamlined, they're more smooth. But turbulent flow, irregular, chaotic motion with eddies. I think I explained eddies one day to you guys. Yeah, maybe as a latecomer, you're not around. So we studied eddies. So yeah, the next. Reynolds number is the dimensionless quantity that predicts the flow regimen. How? When your Reynolds number is less than 2000, we have what kind of flow? Laminar flow. If it's greater than 4000, what kind of flow? Turbulent flow. If it's in between, what's happening? Transitional state. Yeah, transitional state. Okay, this place writes 2300. You see 2000, most times online, but this is still a range, still acceptable. It's not as if it's out of order. All right, next slide. Characteristics of a laminar flow. Look at something that interests me here. Parabolic velocity profile in pipes. Parabolic velocity profile in pipes. What does it mean? When they are in pipes, they tend to initiate parabolic kind of motion. But still streamlined. You understand? That's that stuff you will see like this. All right, no mixing between layers. That means this layer can never come across and mix with this layer. It's not possible. There are smooth layers or very smooth, streamlined. They have low energy. Yeah, so the flow is stable. So velocity profile, if you want to calculate the velocity, sort is what you use. Let's go on. Turbulent flow on the other hand. Well, this diagram I'm seeing here is not for turbulent flow. It's not for turbulent flow. Maybe there was an issue here. So calculation of turbulent flow, it occurs at high Reynolds number greater than 4000. Fluid motion is irregular and chaotic. There are edices and vortices. Yeah, edices and vortices are the spherical, they are the spheres formed during collision between, during the collision between the fluid particles and maybe some obstacles. Maybe some obstacles, including the walls. Strong mixing across layers. Velocity at a point fluctuates with time. Flatter velocity profile in pipes. High energy loss, sensitive to surface roughness and disturbance. Yes. What do you notice here? This does not look like a full turbulence, right? Okay, I give full turbulence. See this thing that fold inward and form your wool. This ones are called vortices. Which ones are just partial curves? Are called eddies. So transition between laminar and that, we know the factors already as it affecting them. It's just that they have a range. That range must exist. All right. Next, turbulence intensity. Turbulence intensity is the measure of the extent of velocity fluctuation in turbulence flow, because it's velocity fluctuation that causes turbulence. You understand? Maybe everything was moving smoothly before, and from nowhere, the particles at the back suddenly develop some kind of extra fast speed. That will cause something like a wave, a disturbance, and the particles might not be able to contain the disturbance, and that will lead to all those turbulence results. It will result in formation of vortices and eddies. So yes, next. Oh, eddies are small circular regions of the fluid formed in turbulent flow due to instabilities and velocity fluctuation. Main flow direction, you see. So type of eddies, we have large eddies, extract energy from the main flow. Small eddies break down into smaller eddies until they're dissipated by viscosity. So eddies actually is what is responsible for mixing. But the moment you have bend like this, you can initiate mixing. Next. Oh, so Buckingham Pi theorem is here. Well, I've treated that already. And in this stuff, I'm not allowed to repeat anything, so I've treated that already. Buckingham Pi theorem. Go back. Just, you know what Reynolds number is? Froude number, that one is for checking hydrodynamics effects. Mach number is for aerodynamics in planes. Euler's number is for turbine fan to check the distribution of air that is closer to that region. Weber number is one I told you about that deals with splash, being able to describe the kind of splash and droplet formations that occurs when something drops into a fluid like water. That's all. All right, very good. So that's all for this one. So we are moving to the next topic. So we've been able to complete the first, how many modules now? 11 modules. And now we are in the 12th module. Okay, it's been great. Let's go on. Where's the duster? Hydrodynamics. I didn't clean it. We've done it. So now, welcome to temperature and thermometry. It's going to be a very long night, but a very impactful one in physics. All right. Okay. So, as you can see, this objective is a real deal. A seriously real deal. We're going to be doing temperature, explaining thermometry, Zerod's law of thermodynamics here, and we're going to be doing thermal equilibrium, explaining that distinguish between temperature and heat. We are also going to be explaining thermometric properties, and we're going to explore thermometric substances, as well as fundamental intervals when we have been able to cover up our temperature scales. We'll look at conversions between temperature. That's what we're going to be calculating a lot, converting from one temperature scale to another. Yep, and explain the construction and working principles of different thermometers. We're going to state the applications, advantage, and the limitations of various thermometers. Solve numerical problems involving temperature conversions. Yes. All right. or set. So, introduction, temperature. So temperature is one of the seven SI based quantities and is fundamental in physics, yes? Right? It's one of them. It's a fundamental quantity. And virtually every physical, chemical, and biological process depends on temperature. True or false? It's true too. So application includes medicine, that's true, we need temperature regulation, right? Weather forecasting, refrigeration, engineering, manufacturing, food preservation, scientific research, and agricultural. Temperature determines whether heat will flow from one body to another body. Yes. So, next slide. So, the definition of temperature. Temperature is the degree of hotness or coldness of the body. More scientifically, which I will advise you keep in your mind, head. Temperature is the physical quantity that determines the direction of thermal equilibrium between two bodies. You know, temperature is also referred to as the what? The measure of the average kinetic energy of a body, right? Please also note that down. It is the measure is the measure of the average kinetic energy of a body. It's the measure of the average kinetic energy of the body. Yeah. Next slide. This is the SI unit. We have Kelvin, other unit degree Celsius, degree Fahrenheit, and the dimension is theta. Yep. So that's that for temperature introduction definition. Next one to look at now is thermometry. Thermometry. Thermometry is the branch of physics concerned with the measurement of temperature. It involves, what does it involve? So in that, we want to learn how to select appropriate thermometric properties suitable for making thermometers. Because before you can be a thermometer, a material can be used as a thermometric material. It has to have good thermometric properties. Then next one, calibrating instrument, establishing temperature scales, and measuring temperatures accurately. You get that? So instruments used is what? Thermometer. So we use the thermometer to run thermometry to measure heat. Temperature, I mean, to measure temperature. Importance of temperature measurement. Temperature measurement is essential in where? Hospitals, chemical industries, food processing, weather, yes, air conditioning, scientific laboratories, and all those things. Those things are very basic. These are basic stuff. Let's fly. Now, temperature versus heat. Want to compare temperature and heat. What's the difference between the both of them? Temperature is the degree of hotness and coldness. That one is measuring how hot or cold the person's body is, right? But heat is the um, transfer of energy due to temperature difference. That's why they call it thermal form of energy. It's going to be transferring energy based on what? Temperature difference. So heat likes to flow from a thermally dense region to a thermally less dense region. That's what I'm saying, from a hot region to cold region. That's the direction of its flow. You get that now? So in terms of units, this guy is measured in Kelvin, SI. This one is measured in joules, right? Now, temperature is an intensive property. Why it is extensive? What does it mean? Temperature is independent on the amount of quantity it is made up of. You get that now? It is independent. But heat is Dependent. It depends on bulk. I get me now. Depends on bulk. Independent of mass. Dependent of mass. That's literally the most same. So this one is measured using a thermometer. Why this one is measured using a what? Calorimeter. Are we together? Yeah, a calorimeter. Are we together then? So thermal equilibrium. When we hear the word thermal equilibrium is the condition in which two bodies in thermal contact. And when we hear the word thermal contact, it does not mean that they are touching themselves, right? It simply means that what? It simply means that what? It simply means that they are in a place or a coordinate that allows exchange of heat. There is no barrier between them necessarily. Even if there is a barrier, the barrier has to be a conducting barrier. You understand what I'm saying? There is no inert barrier or insulating barrier between them. So, thermal equilibrium is the condition in which two bodies in thermal contact have the same temperature. So there is no net flow of heat between them. You get? Example, a hot metal placed in cold water eventually reaches the same temperature as what? As the water. Alright, that's good. So we are going to be taking a short break before we ride on. Is it valid? I mean, 5 minutes. Is it up to 1 hour already? Okay. Alright, we'll be taking a short 5 minute break. All right. So I'm kicking off. Now we're at Zeroth's law of thermodynamics. So what does it state? What does it state? If a body A is in thermal equilibrium with body B, and body B is in thermal equilibrium with body C, then body A is also in thermal equilibrium with body C. Yeah. Now look at this. Look at this. Imagine you have this, this, and this. A, B, and C. And they're in thermal contact. If this body and this body are in thermal equilibrium, are you getting me now? And this body and this body are also in thermal equilibrium with their own selves. What conclusion do you draw about body A and body C? It means that they are also in what? Thermal equilibrium. That's the meaning. Do you get it? So body A and body B are in thermal equilibrium with themselves. Body B and body C are in thermal equilibrium with themselves. So therefore, body B and body C are both in thermal equilibrium with themselves. That means all the three bodies are in thermal equilibrium. You understand? So that's that for that statement. So importance, basis of all temperature measurements, basis for thermometer calibration, and it's how to define the concept of temperature properly. Yeah. So what's next? Thermometric property. A thermometric property is any physical property that changes predictably with what? With temperature. It changes predictably with temperature. Example includes what? Length of a liquid column, right? Now, is that true? How is that thermometric? Can that be validated? Can you validate it? It's validated. You can validate it because we're saying thermometric properties are all properties that what? That what? That can change with temperature, right? So it means that once I heat up that material, or maybe I apply heat to that something, it has a way of reacting to it in such a way we can measure that reaction, that change. I get what I'm saying now. So automatically, the length of a liquid room is one of them because truth is, if I heat up a liquid column, there will be expansion. And that expansion is what? Measurable. I get me now, which makes it a thermometric property. Do you get it now? Now, when you talk about volume of a liquid, if I heat up a liquid, won't it increase in volume? Yes. That makes it also a thermometric property. Pressure of a fixed mass of gas. If I heat it up, temperature affects the pressure of a fixed mass of gas. That is also a thermometric property. Electrical resistance. It will increase. Remember that temperature is directly proportional to pressure. Gay-Lussac's law. So, what about electrical resistance? Now, listen up. When you apply heat to a material, right, a conductor, let's imagine a conductor, what does it do to the conductor? It increases the length of the conductor. And when you increase the length of the conductor, that increase in length does it not support resistance? So that means it increases resistance. Do you understand the concept? It increases resistance. So, thermoelectric EMF, that one does what? Color intensity. Yes. When you iron your clothes, the color becomes sharper. But let's even go beyond ironing. There is no metal you are going to put in fire that is not going to glow after it has stayed there for long. And the longer it stays there, the longer it will be, the more it will be glowing, like that redness, right? You experience that more in metallurgical industries. Yeah. So this is defined. So yes. So we have radiation emitted, right? So in radiation, there are some materials that's thermic emission and all those things. They emit radiations, right? That's inversely proportional to temperature. You see, it's very possible, yes, conductivity, since we mentioned resistivity. You understand that? Yes. So characteristics of a good thermometric property. Characteristics of a good thermometric property. We have what? Varying uniformly with temperature. Varying uniformly with temperature. Yeah. Then must be highly what? Sensitive. You don't know when they say it's highly sensitive, it measures the slightest changes in temperature. It reacts significantly, visibly to temperature change. Do you get what I'm saying? So that's just it. That's it. Be measurable accurately. It must be measurable accurately. Easy to measure accurately and must respond rapidly. Do you understand that? Must respond rapidly. So, respond rapidly, it must be reproducible. That means when I run the measurement the first time and run it again the second time, I should be able to get what? The same results. I should be able to get the same results. So, um, cover a wide range, a wide temperature range, and must remain stable with time. You understand? You don't want something that after just a short period of time start disintegrating by itself. You don't want those kind of stuff. You understand? So what next? Next. Geometric substances. Geometric substance is the material whose physical property changes with temperature and is used in metal construction. You understand that? So basically, just hold on now. Listen. For something to be a geometric substance, it has already passed the first phase of exhibiting thermometric properties first. One or two thermometric properties that is measurable. Do you understand that? Good. Aside from that, the physical presentation and character of that material must be tested alongside with its safety. You understand what I'm saying? So those are things that we'll check before utilizing or accepting a particular substance as a thermometric substance. Do you understand what I'm saying? So example of thermometric substance: mercury, alcohol, platinum, hydrogen gas, semiconductor materials. Every single one of them, if you look at them carefully, you can easily pinpoint one or two things that makes them fall in this list. Mercury has high tolerance for high heat without getting decomposed. Alcohol is a good conductor, so it's also sensitive to heat. Platinum is a wire, right? Is a conductor. You can use it to even measure if you are doing resistance, thermometer, and all those things. It's utilizable. Then hydrogen gas in your gas thermometer, utilize it. And then semiconductor materials. Yes. So next, characteristics of a good thermometric substance. So a good thermometric substance must be what? It should it should possess uniform expansion. It must be what? Highly sensitive. Must show high sensitivity. Then what else? Chemical stability, non-reactivity, right? But we don't want it to just react anyhow because it's reading temperature, and if it's read heat, if you expose it to heat, as a reactive something, it might end up reacting and that will cause issues. You get? So, but again, it must have a very low freezing point and a very high boiling point. Why? Because the one of low freezing point wants it to be able to measure what? Very low temperatures. Want to measure, be able to measure very low temperatures. Then the high boiling point is because we want them to be able to measure high temperature without vaporizing. You understand? Yeah. So, easy visibility. And that's an advantage mercury has over alcohol. Do you understand? That's an advantage mercury has over alcohol. Mercury is opaque. So it's easy for you to view it and identify the level it is. Yeah, quick response. Okay. Okay. Fixed points. What are fixed points? You see, your fixed points are points that have been accurately obtained from a thermometric experiment to be calibrated in a thermometer. And those points are usually made up of your upper limit and your lower limits. The distance between fixed points are referred to as what? Temperature interval or scale intervals. So your upper fixed point is the point where during the experimentation they found out that that point there is going to be the what? Steam point or the boiling point. While the lower one is the one that we are going to be calling the what? Melting point or freezing point. So that's it. For example, for the temperature scale, for example, for the Celsius scale, what do we have? Upper fixed point, we write it up here. Lower fixed point, we write it here. For your temperature scale, upper fixed point is degrees Celsius. This one is 0 degrees Celsius, Abi. But if it were to be for Kelvin, the upper fixed point that is equivalent to 0 on you know that's our boiling point, Abi. That's equivalent to 100 is what? 373. Why this one is 273? You get it? Then we have another one again. That Fahrenheit. That one is what? 212. And down here is what? 32. But the scale difference between the upper fixed point and the lower fixed point is what we call what? So-called scale interval SI. People need sleep. Do you get that now? Do you get that now? So that's that for that. Measure the standard atmospheric temperature. All right, next slide. Next slide. Fundamental interval, that's what I spoke about. That's the scale interval. The fundamental interval, okay. The fundamental interval is the temperature difference between the upper and the lower fixed point. So for your degrees Celsius, your fundamental interval is 100 minus 0, which is what? 100, Abby. Then for your Kelvin is what? It's still 100, but for your Fahrenheit is what? 180. Yes. Interesting. So that's it. Next. Temperature scales. So there are 3 commonly used temperature scales. If you are a book, you can go and learn 20 more. It's 3 they used to do. So there are 3 major temperature scales. Yeah. And what are they? We have others actually. Yes, we have like Rankine, we have degree Newton. I didn't make a mistake. Degree Newton is a temperature scale. It's one of the oldest temperature scales. Understand? So, but yeah, we are utilizing these 3 major ones. Celsius scales. Well, it is more accurate not to just call it Celsius. It is called degree Celsius. And that Fahrenheit is called what? Degree Fahrenheit. And then the Kelvin scale is called what? Degree Kelvin K. They agree with degree Kelvin. Kelvin is the name of the person. It's the name of the person. So you don't add degree to the name of the person. That's why Kelvin does not have degree. Do you understand? Fahrenheit is what? Eh? Nobody. So if what I mean is that it does not mean that that thing cannot be the name of the person somewhere. But like if the name of the scientist was was Fahrenheit, you cannot put degree Fahrenheit on that name if you want to use it. But nevertheless, that's not a bone of contention, right? So next one, next slide. Slide. Let's talk about it. Let's talk about it. So listen, everybody. The Kelvin scale is the SI temperature scale. I will call it. They call it absolute. No, they don't call it absolute zero. That's the absolute scale. So when you hear what absolute zero is 0 Kelvin. It's 0 Kelvin. Do you understand? That's what absolute zero is. 0 Kelvin. So next, absolute zero is the lowest possible temperature you can have in your normal ideal system. So what are the characteristics of your absolute temperature or absolute zero scale? There is minimal molecular motion, there is zero kinetic energy, cannot be reached experimentally. So you hear someone say, person is at -4 degrees Kelvin. It's not possible. It's an impossibility experimentally. But I don't believe in the impossibilities though. Tomorrow you hear that somebody has done it. And it will enter the books. And everybody will now change their edition and bring new edition. The meaning of new edition means I never said it. So, next. Relation between temperature scales. So, yeah. 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 So, at this point, I would have needed the headphone. So watch. We have this 100 degrees Celsius. And what is here? What's here? 0. Kelvin is what? Sorry, Fahrenheit. So what we are going to do? Let's imagine that we put an unknown here. We mark this place unknown, but we know it is measuring a particular degree Fahrenheit measurement, right? Let me just call it, let's do it this way. We know that this place is Fahrenheit we are measuring here, right? Are you getting what I'm saying? Hello? And let's assume that this side, it is Celsius we are measuring. We know that it's Celsius. Let me just write it on top here. I know why I said that, so that I can record here as degree Fahrenheit and degree Celsius. So there's an unknown mark here. I want to know what relationship exists between Fahrenheit and Celsius. How do you do it? This technique is exactly the way you also solve for any other question that has to do with relationship with temperature. Up minus down, now I mean 100. Year minus year, that's how many degrees Celsius, equals to up minus down again, year minus year, minus 32. Now let me tell you something. Some of you will not be in the hall wasting time. And the man said up first. Is it up or middle first? You can start from anywhere. You can do middle minus down and do up minus down. So anyhow you do in the left is how you do in the right. Are you getting what I'm saying? So yes, yes. Let's cross multiply. 180 degrees Celsius equals to 100 degree Fahrenheit minus 200 like this. Abi. So let's divide through by 100. Two here and 9, 2 here and 5. So yeah, what are we left with? 9 over 5 degrees Celsius equals to degree Fahrenheit minus what? So this is the relationship. So it means that if I want to find degree Fahrenheit, just use the expression degree Fahrenheit is equal to what? Carry this one here. 9 over 5 degrees Celsius plus 32. So it means if I want to know what 30 degrees Celsius is in Fahrenheit, just for me to put 30 here. Do you understand? So I'll be saying degree Fahrenheit is equal to 9 over 5 multiplied by who? 30. 5 here now 1, 5 here now written 6 plus 32. Abi? So what do we now have? Degree Fahrenheit is this one times this one now written. At 54 now. That gives us 86. So that means 30 degrees Celsius is equivalent to 86 degree Fahrenheit. Are we good? All right. Let's move to the next slide. Example 1. Convert 32 degrees Celsius to Kelvin. Oh, sorry, convert 35 degrees Celsius to what? To Kelvin. How do we do that? When they give you anything at all, you ask yourself, they want you to convert something in Celsius to Kelvin, Abi? So you draw something like this that is dealing with Kelvin and what? Celsius. So something like this. So we have what? 35 here. No, up is, they are relating one Celsius and Kelvin, Abi? What's the upper of Celsius? 100 degrees Celsius. This one. Abi, this then we are comparing with Kelvin, Abi. Kelvin. And 273. So what value is it? 35, Abi? Degrees Celsius. I know 35 degrees Celsius is around there. Just locate it. 35 degrees Celsius. In this place, column written X. And one fine written AB. So as usual, that thing, anyhow you like. 100 minus 0, 100 over 35 minus this one, 35 is equal to this minus this one now written 100 divided by X minus 273. If you cross multiply now, this one and this one give us what? 100x ahead. I don't want to do it like that. Equals to 35 times 100, Abi. So 100 to cancel. I can cancel it here. X is now equal to what? 35 plus 273. X is equal to what? X equals to, when we add it, what's that? 308 Kelvin. Do we get it? 30 Kelvin. That's why for Kelvin scale, we used to tell ourselves, if they give you something in Celsius, you want to convert it to Kelvin, just add 273 to it. That's a shortcut instead of doing this. I just did it so that everybody can see the procedure, because eventually in an exam, they might give you they might even give you a temperature scale you've never heard in your life. And they will give you the upper limit and the lower limit. So you must do this. Yes. Hey. Yes. Example 2. Thermometer. So what's a thermometer? A thermometer is an instrument used for measuring what? Temperature. Are you getting me now? It is used in measuring temperature. Good. So, what's the working principle of a thermometer, please? The working principle of a thermometer is that what? Every thermometer operates by using a thermometric property that changes with temperature. Do you get that? Do we get that? So, next slide. Next slide. Working principle, expansion of liquids, for example, types. Now, we use those ones for liquid in glass thermometer. You understand? You know, we have liquid in glass thermometer. So obviously, those liquid are thermometric liquid that can expand with temperature change. You understand what I'm saying? They can expand with temperature change. So yes, we have mercury in glass thermometer and alcohol in glass thermometer. So what are the advantages of this liquid in gas thermometers? They are simple, reliable, and inexpensive. But what are the limitations? They are fragile and limited range. They only measure short range temperature. I get me now? They only measure short range temperature. Next. Next. This is where we have been moving. This is where we are. Sources of error in thermometer measurement. Number one is parallax error. How many of you know parallax error? What's parallax error? So basically, parallax error is when you're not taking reading from the appropriate height. You're supposed to take your measurements from perpendicular to the site and the level that you are reading because of the meniscus most times. Another reason is because of binocular vision. So all those things, to control them, your eyesight has to be on point. Rather for those that have 4 eyes, God will help you. Poor calibration. Those are some of the errors in temperature measurements. When the calibration is poor, you understand? We're not seeing the calibration well, or there were errors in the calibrations. Yes. The endpoint error. Endpoint error is one common error when it comes to calibration. Endpoint error. Even in many meter rules, there are endpoint errors. You see a meter rule, you will see where the road is zero, meaning that the zero did not start from the beginning. There is one small length there. Incomplete immersion. That's maybe you want to measure something and you didn't measure and put the sensitive part of the thermometer, maybe the bulb or something, into the material you're measuring to give you inappropriate readings. So we see another one where they delayed equilibrium. So when there is delayed equilibrium, you understand, between, because there needs to be an equilibrium between the thermometric material and you and the thing it is reading. Once it's delayed, it needs to be getting lost at the same time and the reading become non-consistent. Instrument defect, common. Experimental interference, another common one. You are doing your experiment, the lab attendant comes to come and interrupt you. And you accepted the interruption because it's a lab attendant, you want to receive it. Sometimes those things only distract you more and you make more errors. Next slide. Precautions. What I tell you, read at eyes level. allow sufficient time for thermal pressure. Use the appropriate thermometers. Avoid touching the bulb. Very, very, very important. Keep the thermometer, the handle glass thermometer carefully because they are fragile. Application of thermometry. Application of thermometry. So you see, we use it in medicine, meteorology, chemical industry, food, and all. We mentioned this earlier. Please, next slide. Formula summary. So we've done all this. Next slide, except from that last one there. Let me go back. So you see that last one there. R is equals to R naught open bracket 1 plus alpha. You see that that's the relationship between the resistance and temperature. Next. So students will be able to do all these things. Lesson summary. This is the end of this part. And really, that's how short it is. That's how short it is. Temperature and thermometry is like a foundational class into thermal physics. So physics branch. See how wide it is. The scope is wide, and the topic, physics as a topic, is a wide thing to do. And now we are moving into like a theme on its own, which is like thermal. So we're going to hit it and come over. Sharp. Okay, so next slide. Heat and energy, fundamental. All right. So let's go. This aspect needs a lot of calculation. It needs a lot of demonstration and all. Okay. So yes, what is energy? What is energy? Very simple, yeah, that's it. Energy is the capacity of a body or a system to do work. The ability, capacity of a body or system to do work. Without energy, there will be no physical, chemical, or biological process. None of them will be able to occur. And everything that happens in nature involves energy transfer, ranging from walking to cooking to power supply to planting. Everything involves work. So, what do I have now? Everything that happens in nature has to do with energy. SI unit of energy is what? Joules. And it's named after James Prescott Joule. Other units of energy, we have calorie, we have kilocalorie, electron volts, kilowatt hour. All right, let's move in. Forms of energy. Forms of energy. So energy exists in several forms. We have mechanical energy, which is divided into kinetic and potential. We have thermal energy, energy possessed because of random molecular motion. We have electrical energy. Electrical energy is produced by movement of electric charges. Chemical energy is stored inside chemical bonds, and they are usually available in foods, batteries, and so many other. You get that now? So, so Law of conservation of energy. Now, energy can neither be created nor destroyed, but can be converted from one form to another. That is the law of conservation of energy. That was the law of conservation of energy. Is this the next slide? So now we're looking at heat. What is heat? Heat is a form of energy, right? And we know it is a form of thermal energy. Heat is a form of thermal energy. Heat is a form of thermal energy. I get you now. That is, and when we say it's a form of thermal energy, it means that it has dependence on what? On temperature. It has dependence on temperature. It has dependence on temperature. Do you get that? All right. So that's what makes it thermal. And again, this guy depends on temperature difference. Temperature what? Difference. So if I have a surface here that was 100 degrees Celsius, and I have another surface here that was 0 degree, or let's say 10 degrees Celsius, right? What will I be expecting? I'll be expecting heat transfer from the 100 degrees Celsius on to the what? 10 degrees Celsius guy. Do you see that? So that's it. That's it. So that's it. Next. Go back. Heat is not contained inside a body. Instead, heat exists only during transfer. I see that now. So once transfer stops, the transferred energy becomes part of the body's internal energy. Very important. That's a very, very important thing to note. Very, very important thing to note. All right. So, next slide. Next slide, please. Molecular explanation of heat. Every substance consists of what? Atoms and molecules. That's where we start from. They all have atoms and what? Molecules. Now, these particles are always doing what? Moving. We know it. Particles are in constant motion. They are always moving. The faster they move, the greater their what? Kinetic energy. We know that they have kinetic energy. So kinetic energy is the energy possessed by the body by virtue of what? Motion. Right? So if you see something moving faster, it means that that guy has a higher kinetic energy. Now, he said greater kinetic energy means higher temperature, because temperature is the measure of the average kinetic energy. Do you see how this thing is moving like a chain? Now that we know that because of temperature is the measure of average kinetic energy, so therefore we now know that okay, that it means that it is being measured by temperature parametrically. So when heat now enters a body, the molecules will do what? Vibrate faster. And what will they do again? They will collide more frequently. You see that? You see that? Possessing greater average kinetic energy. So the whole thing is like a chain, and it's a very interesting chain. See, you have, you have, you have, you have a body. See, oh, this body, you heat it up. You did what? When you heat it up, in the act of heating it up, what were you doing? You were inducing kinetic energy. You were inducing what? How? Because the molecules were, what does kinetic energy do that make the particle free? Kinetic energy increases what we call the DOF. You can tell me what DOF is? The degree of freedom. We will discuss that when we get to ideal gas. The degree of freedom. When it increases the degree of, how does it increase the degree of freedom? By breaking bonds, right? By weakening bonds or breaking bonds. Now, when it increases the degree of freedom, what's the next thing that it wants to do? That will cause the molecules to be free. Molecules becomes what? Free. Abi? When molecules become free, what's the next thing that we're going to be seeing? We're going to be seeing rapid movements. Rapid what? Movements. And these movements, we're going to see it as what? Vibrations. You know, in solids, if it were to be solids, we see it as vibration about their mixed. If it's a solid, we see it as vibration about their main position. If it were gases and liquids, they would have probably started evaporating and stuff like that. But this one, I'm going to put it there in bracket. If what? Solid. We see the vibrations. Then we now have what? From there, we now have what? Yes? Anybody? What do you think will happen? This rapid vibration is what temperature is reading. It's what temperature is reading. Because temperature is the measure of the average kinetic energy of the body. So it is literally reading how the rapid motion is occurring. I get me now? So you see now that that is the chain. This is the chain of heat. You have a body, you heat up the body. The body is, that heat is inducing kinetic energy, and that causes a higher degree of freedom. Molecules become free. There is rapid vibrations and movement, and then we have temperature rise. And this temperature rise can now be measured. Can now be measured. Yes, so that is it for that. Next slide, please. Internal energy. When we hear the word internal energy is simply the what? It is the total microscopic energy possessed by all molecules. Are we together here? It is the total total macroscopic energy possessed by all molecules. Do you get that now? Internal energy. That's internal. What does it consist of? Your internal energy is made up of mechanical energies. You will see it, molecular kinetic energy and molecular potential energy. Those are the things that make up your what? That make up your internal energy. What's the symbol of internal energy? U. And what's the unit? Joules. Are we together here? All right. Internal energy increases when heat is what? Supplied. Work is done on the system. Remember, that's we're trying to explain what this heat supply means. Whenever heat is being supplied, it means that work is being done on the system. If it is getting lost from the system, it means the system is the one doing work on the surrounding. Are we getting what I'm saying, please? So do we get what I'm saying? It's very, very simple. Next slide, please. Next slide. Next slide. Next, we've done this. What's going on here? All right. Heat always flow how? Naturally. From where to where? From thermally dense regions to thermally less dense regions. Thermally dense regions to thermally less dense regions. These dense regions are your what? Hot regions. These ones are your cold regions. Do we jig? Do we get what I'm saying? Do we get what I'm saying? So that is it. So this is the channel of heat flow. That is what heat likes. You can see the illustration here. Are you there now? Are you seeing it now? And again, can heat ever flow? Can heat ever flow from a cold place to a hotter place? Can heat ever flow from a cold place to a hot place? Yes, it can, but not spontaneously. There must be the presence of an external work. There must be an external factor. Do you understand what I'm saying? This is what I'm saying. There must be an external factor to do that. It can't happen by itself. All right, very good, very good. Without wasting much time like this now, go to the next slide. What are the factors affecting heat transfer? After we talk about the factors affecting heat transfer, we need to talk about the things that heat is doing to us too. We need to check the effect of it on us, especially in this country. We need to know what's doing us. Factors affecting heat transfer. Amount of heat transferred depends on what? Mass. It depends on what again? What again? What again? Again, and again. These are the things, factors that are affecting heat transfer. Now let me explain the meaning of this statement. This thing is not that they look like this, right? Let me quickly present to you what factors that actually affect heat transfer. Because if they ask someone, how does time affect heat transfer? You need to give what I'm trying to tell you now is that I think there were errors in this particular slide. Yes. So, the factors that affect heat transfers is dependent on what kind of heat transfer you are talking about. We have how many forms of heat transfer? 3. What are they? Conduction, convection, and radiation. Now, if it is for conduction, the factors that will affect heat transfer by conduction, those guys, who are they? They are temperature gradients. Under temperature gradient, there are 2 people inside. Thickness and temperature difference. What again do we have in this category, please? What again do we have in this category? We have area, cross-sectional area. Cross-sectional area. We have nature of conductor. And this nature of conductor, in brackets, we are talking about thermal conductivity of the material. Every material has a different thermal conductivity. That's important for you to note. Now, the whole of these things here, what law describes the factors affecting heat transfer by conduction? They call that law the what? They call it the what? What law is it called? Nope. It's called the Stefan-Boltzmann's law. What am I saying? Sorry. It's called the Fourier's law. The Stefan-Boltzmann's law is for radiation. Are you following what I'm saying? We call it the Fourier's law. The Fourier's law. You know that Fourier's law, there's an intertwine in the Fourier's law because Fourier's law is actually a series in the radiation spectrum. It's a series. You know what I mean by a series? It's formed from the movement of electrons from a particular energy level to another energy level. I get what I'm saying now. It's part of the series. Yeah, the Fourier series is the 12th series. But let's not go there. So that be okay. Now, what about if I want to mention those that affect convection? We'll be talking about area. We'll be talking about area exposed. The area exposed. Are we talking about now? We'll be talking about temperature. Talking about temperature, both the temperature of the environment and the temperature of the fluid. We'll talk about that. We'll talk about the property of the material. That's where we're going to be expatiating and elucidating on points like what? On points like your coefficient of convection. Your coefficient of convection. The coefficient of convection. So, what other things do we have there? We have, okay, I've mentioned area. So we are also going to be looking at what? Also going to be taking cognizance of your, this one is area exposed, of the area in contact. Area in contact with fluid. With the fluid. This one now, which law explains how this one occurs? Newton's law of what? Of cooling. What do I call it? The law of cooling. Newton's law of cooling. Now, for radiation, who are the people in this one? We'll talk about emissivity. Emissivity. Are we together here now? Emissivity. We'll also talk about which one again? We'll talk about temperature. That one is always there. Temperature. We'll talk about temperature. We'll talk about the nature of the material. Why? Because of Boltzmann constant. Boltzmann constant. This Boltzmann constant is why we say nature of material. Nature of material. We'll call it Stefan Boltzmann. We'll also talk about the area exposed. You see it? This their rate of heat transfer is not something you can write like this. Do you understand what I'm saying? Understand me very well. It's not something you can write like this. It's not something you can write like this. This is how to present it, like this. I get what I'm saying now. Because some of the things written here now, they don't have like mass. Mass doesn't have anything to do with heat transfer. Like literally. Like affecting the transfer of heat does not have anything to do with it. So did you see mass in any of the thing here? No. So which law explains all these ones here? We call that one what? Stefan Boltzmann's law. Now, the question I want to ask you is this. We have Boltzmann, we have Stefan Boltzmann. Under what aspect do you hear of Boltzmann? When we are talking about what? When we are talking about VRMS, all those, when we're talking about the relationship between average temperature, average kinetic energy, and temperature, you will see normal Boltzmann there. That one naturally has a way it relates with who? It relates with Avogadro's number. What's the value? 1.38 times 10 raised to the power of what? Minus 23. But when you're not talking about the Stefan Boltzmann constant, the one that controls heat flow by radiation, you're talking about a value of what? 5.67 times 10 raised to the power of what? Minus 8. These are constants that must sync your head being your head. Sink your head and be in your head. So that is that for that. So we have this thermal reservoir. A thermal reservoir. So what's a thermal reservoir? A thermal reservoir is a body with very large heat capacity. Do you understand that concept? Do you understand that concept? It means that it's a body that has the capacity to contain large amounts of heat. The sun is a perfect example of a heat reservoir. Trust me. The amount of heat the sun contains, in fact, it now looks like it is he that is producing the sun. I mean, sorry, it is he that is producing the heat. But literally, is it the sun producing the heat? Well, the sun is just fortunate that the gases that are meant to do all those heat productions are more concentrated in that side. Hydrogen, helium, and all those things. And that's why the sun, you can't say the sun is a real material because if you go, I've not gone there, but scientists make us understand that it's not something you can touch. It's gas. You can't hold it. It's radiations constantly reacting. Heavy level nuclear fission are constantly happening there. You can create the sun in your house. China, by the way, created the sun that is hotter than the sun there. I don't know why, but they did. The one in this one is hot enough to create one beside your backyard. So yes, let's move. Tell us about. We are looking at very large heat capacities. Its temperature remains practically constant while exchanging heat. It's better learn. That's one of the characteristics of the thermal reservoir. Even when it is changing heat, it is what? It is practically constant. When we say practically constant, we're saying that the temperature is not even changing, but it is exchanging heat. Do you understand what I'm saying now? Now, we have examples, the ocean, the large lakes, and the atmosphere. Do you get that now? The ocean, the large lake, and the atmosphere. You want to ask me a question? Yes? Did I what? Did which laws? Which laws? Okay, the Fourier, all these laws. We have not even entered there. We'll also enter it transfer. When we enter it transfer, we'll state all the laws. We'll talk about the applications of these things now. Yes. So yes, next slide, please. Heat as molecular motion. Imagine heating water initially. Molecules do what? Move slowly. As the heat enters, their speed increases. Collision becomes more energetic. What do we mean by collision become more energetic? The collision is becoming more what? Is now generating more kinetic energy. I get what I'm saying now. Is generating more kinetic energy. So what do we have next? Eventually boiling occurs where molecules escape as what? As steam. Yes. All right, next slide. Unit of heat. What are all the units of heat? Joules, older units are calories and kilocalories. So you have your food energy, usually expressed in kilocal today. Next. If you supply 5,000 joules, how much is going to be transferred? 5,000 joules. Be pressing the next in this slide. Let me see something. Just pressing next. Keep pressing next. Keep pressing next. Keep pressing next. Press next. Continue. Just be pressing next. Continue. 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 All right. Continue. Interesting. Continue. I'll go back to where we were. So yes, we have this. Is this where we are now? So a block has its capacity of this. How did we get here? Go back. But you know what? Just hold on. Now I'm going to teach you something before we continue with the slide. There are some things that are absent. There are some things that are absent there. Yes, now watch me. What I want to talk about now is thermal expansion. Thermal expansion. What is meant by thermal expansion? So after thermal expansion, are you there now? After thermal expansion, are we together? After thermal expansion, we are going to be doing what? We are going to be diving into after thermal expansion, we will enter heat capacities. After heat capacities, then we will now enter where? Heat transfer. Then we will now know that we are done with the first part of heat. Now let's go. What's the meaning of thermal expansion? Yes? The meaning of thermal expansion. Thermal expansion describes how materials change in dimensions. Change in dimensions due to what? Due to heat application. So when you apply heat to some bodies, I get to now. When you apply heat to some bodies, then the heat will cause a change in the dimension of the body. That's one of the effects of it. One of the effects of it is what? Change in dimension, right? So good. So yes, we have that. Change in dimension due to heat application. Now this thermal expansion are of different types, right? We have three main types. We have the linear expansivity, then we have the area, also known as the superficial expansivity, then we have the what? The volume, also known as the what? Cubic expansivity. Do you see that now? So we are going to go through this. When we are done going through this, we'll talk about what? We'll talk about anomalous expansion of water. Explain the nitty-gritties of that and how they usually affect the density and the volume of water at specific temperatures. Are we together here? So let's go. From here, we can easily tell ourselves one big truth, that thermal expansion of three categories. We have the linear expansion, or called the linear expansivity. So let's start with that. What's the meaning of linear expansivity denoted as alpha? What does it mean? Linear expansivity is the what? Change in length per unit length per degree rise in temperature. This definition is one of the definitions that most science students used to first know in their life. That is. So in the equation form, what does it stand for? We have this is equals to what? L2 minus L1 over L1 into bracket theta 2 minus theta 1. Then we know how this theta minus, it simply means what? This is equal to change in L over L1 change in theta. Do we get that? What's the unit of linear expansivity? Per Kelvin, because up here is meters. This one will cancel this one. Then we're left with per Kelvin. Is measured in per Kelvin. Do you see that? It's measured in per Kelvin. Now, as we know that it is measured in per Kelvin, the next thing we want to check out now is what? Area or superficial expansivity. Now, what's area expansivity, please? Area expansivity is what? Change in area per unit area per degree rise in temperature. Are we together here now? A degree rise in temperature. So what are we now having? We're having what now? It's denoted as what? Beta. So I'm saying now that beta is equals to A2 minus A1 all over A1 into bracket theta 2 minus theta 1. So that's the same thing as what? We're having change in A divided by A change in what? Theta. What's the unit? Measured in what? Per Kelvin. Do you get the concept? So that's for area. Now we now want to go into what? Volume. Also known as what? Superficial. So I wrote superficial, sorry. Cubic expansivity. Now, what's the meaning of, what's that one? Is the what? Increase in volume or change in volume? Yes. Per unit volume per degree rise in temperature. Yes. So what do we now have? This one is measured in gamma like this. We have this equals to what? We have V1 into bracket theta 2 and the theta 1, right? So it is still measured in per Kelvin, right? And then this is still written as change in V over V1. Change in what? Theta. Now, let me quickly introduce you to something. How many of you know that a deformation is occurring during this process that is almost elastic? What's the meaning of elasticity? Elasticity is what? To return to its original dimensions after. So, an elastic material is one where you expose it to a distortion, it gets deformed, but the moment you remove the external force that causes the distortion, what will happen? The deformation is reversed. That's the same thing as we know here. When you heat up a material, what do you notice? When you heat up a material, what do you notice? I didn't hear you. When you heat up a material, it will expand, I mean. When you remove the heat, what will happen? Contract. That means this bro too, they experience what we call a strain. And that's what many students don't see. Listen to me. In this formula here, is there something you are seeing Genuinely speaking. That reminds you of what? Of bulk strain. Bulk strain. So it means that in this expression here, we can see bulk strain. Right? Good. Let's do something quickly. Strains. Thermal strains. What are the thermal strains I can see? From linear expansivity, I can see that I have change in L over L, which is the inverse of what? You know, normally it's supposed to be, yes, this is even not even inverse. This is the strain direct. What strain is this? This is your tensile or compressional strain, which I told you it's better I just call it longitudinal strain. Are you guys what I'm saying? We have longitudinal strain here. We have longitudinal strain. Now, let us check something. Young modulus is equal to what? Stress over what? Strain. Meaning that strain is equals to what? Stress over Young modulus. Abi, do you know that we can therefore bring a relationship between this thermal strain that was caused by heat and Young modulus? So it's just for me to now carry, anywhere I see my strain in this formula, I'll put stress over Young modulus. That means linear expansivity can also be equal to what, please? Stress, Abi, stress divided by Y change in temperature. No strain again. We have substituted strain. This is strain. Theta, I'm sorry, change in L over L. That's the rule of strain. So strain, anywhere we see strain, we are putting what? Stress over Y. You see that now? Which means that you know that this stress here is force over weighting area. Abi? So if you want to really do it, it means this guy is equal to force all over AY change in theta. Do you see that now? Are we seeing that now? So it means that force can be equals to linear expansivity AY change in theta. Do you see that? This is the relationship between the linear expansivity and a modulus. It's a relationship. It's a relationship. It's a relationship. It's a relationship. Mm. So that bulk, it can also happen with bulk modulus. It cannot happen with area. So what do we have for bulk? Anywhere I see change in V over V, that is a what? A strain. And it's supposed to be equal to what? Bulk stress and bulk stress na pressure. About bulk modulus. What do you use to use and represent the bulk modulus? B. Easy peasy. Just carry that formula that is there, that is lonely. Because that's a lonely formula. Just carry it and put where? And put it inside here. Carry that lonely formula there. Where is he? Where is that guy? The lonely man. Right. That this equals to what now? B all over B change in theta. So pressure is equals to YB change in theta. Why am I even calling it Y? Okay, yes. So sharp. That is what it is. It is what it's going to be. It is B. So yes, it's sharp. It's very, very sharp. Okay. So from here now, we can now dive into anomalous expansion. Anomalous expansion. Anomalous expansion. What's the meaning of anomalous expansion? The abnormal pattern of expansion, right? The abnormal pattern of expansion. Are we together? Are we together? The abnormal pattern of expansion that exists. So, what's that abnormal pattern of expansion that exists when it comes to water? Because it's water that experiences anomalous expansion. So, what's it about? It's about what occurs between the temperature of what to what. You can tell me? Well, something goes on 0 degrees Celsius to 4 degrees Celsius. Now, normally, whenever you heat up a material, what do you expect to be happening? The material is supposed to be doing what? Expanding. But water, when you're heating up water, maybe you have water at 0 degrees, when you're heating it up to 4, it's not water to be expanding because you're heating it up. Water is contracting. It's contracting. Are we there now? And the more it contracts, are you there now? It will continue contracting until you get to that 4 degrees Celsius. And you agree with that when we say it contracts, what's happening? Its volume is becoming smaller. Its volume is becoming what? Smaller. So that means when it finishes contracting by 4 degrees Celsius, its volume it would have attained minimum volume. So water experiences minimum volume at 4 degrees Celsius, right? And anywhere you have minimum volume is where you have maximum density, because density is inversely proportional to volume. So here you have your minimum volume or your maximum density. So from 4 degrees Celsius, what now happens? It starts expanding normally, and when it gets to 100 degrees Celsius, since it's expanding normally, this way it's going to have is maximum what? Volume, but minimum density. You have to note that down. These are very, very important things you should know. Very important. Yes. Okay. Okay. Now, we can move to it, to heat capacity. And move to heat capacity. There's a poster. Okay. Thank you. So yes, heat capacity. Heat capacity and specific heat capacity. When we hear the word heat capacity, what comes to our mind? Or specific heat capacity, what comes to our mind? Specific. Exactly. So, specific heat capacity, it is the amount of heat required to raise the amount to raise the temperature of a unit mass of a substance by 1 Kelvin. If you have 1 degree Celsius, they'll still mark it for you. Are we together here now? Are we together here now? So from here now, we have an expression we are common conversant with, which is what? MC change in theta equals to what? H. Where C is what? Specific heat capacity. What's the unit of specific heat capacity? C is equals to H all over M change in theta. So what's the unit? Joules per kilogram per Kelvin. Are we together now? I didn't know retweeting. No retweeting Jones. All right, so yes, we've talked about specific heat capacity. Now, heat capacity. Heat capacity. So for this heat capacity now, what do we have? The same thing, no? Heat capacity is the amount of what? Heat required to raise what? The amount of heat required to raise the temperature of the whole body or object by what? By 1 Kelvin. What's the formula for that one? What's the formula for that one? C equals to what? Capital letter C is equals to M small letter C. Yes. But now, Let's do something. We know that times C is equals to capital letter C over M. Is that not it? So I can substitute it inside here. Do you get what I'm saying? And if I substitute it inside there, or I can just bring that C as that down here. What would that give me? I mean H over what? Over M change in theta to be equal to what? C over what? M. M cancel M. What am I left with? H is equals to what? Change in theta C. Or C change in theta. What does this C stand for? Heat capacity. Where you can see that H, you can see that C is equal to H all over change in theta. Are we together? So therefore, if you want to calculate the unit is what? Joules per what? Kelvin. Joules per Kelvin. Yes. Joules per Kelvin. All right. So what do we now have next? We are now going to talk about latent heat. Latent heat. I'm coming there, just hold on. Latent heat. What's the meaning of latent heat? Latent heat is the hidden heat, I mean. That's what they call it. We use the word hidden heat. It is the what? It is the heat that causes a change in state of a body without a change in temperature. Are we together here now? Now, there are different types. We have what, and what? We have latent heat of fusion, latent heat of vaporization. We also have latent heat of sublimation and all those things. But don't worry about those ones. Not for now. We have latent heat of fusion as well as latent heat of vaporization. Do you understand that? All right. So, what is the meaning of latent heat of vaporization? That one is when what? What's that one for? Latent heat of vaporization. Is the what? It is the heat required to cause a change in state, sorry, since we are really specific, we are talking about the F, latent heat of fusion, to change a what? A liquid into a what? Solid without change in temperature. Without a change in temperature. That's it. Without a change in temperature. That's latent of fusion. But when you're talking about the latent heat of vaporization, I'm looking at the one that's going to cause a change, that is heat required to cause a change, but it's not even to cause, heat required to change, in English, to change a liquid into a gas, to change a liquid into a gas without change in temperature. Without change in temperature. All right. So, to explain and buttress on this thing here, all right. Okay. So, yes, we've done the latent heat and we've done that. So, imagine we want to move, we want to change ice at minus 10 degrees Celsius to steam at 120 degrees Celsius. To do that, they will ask you to calculate the total amount of heat required to change ice at minus 10 degrees Celsius to steam at minus 20, or to steam at 120. You know, normally the steam point is 100, but now they now want you to change it to like 120. It will take a series of drives, a series of steps. That's what I'm saying. And what's that series of steps? You have to make sure whenever you get to their site of, what do you call it? Yes, there's when you get to their site of change in state, their site of fusion or evaporation, you have to make sure that you acknowledge those places. Now, for example, the journey will start from ice moving, this ice turning from ice at minus 10 degrees Celsius, Abi, to what? To, I don't minus ice. To ice at what? 0 degree Celsius. Yes. Now, at this point now, it is still ice at 0, Abi. What do we now convert it to now? It will now turn steam. It's not open up. Then we turn it to liquid at 0 degree Celsius. Are we together now? Then from here, we will now turn it to what? It's now a liquid at 0. We will now turn it into what? That is liquid at what? Before we will now turn it to what? Steam at what? 100 degrees Celsius. Then we will now turn it to what? Steam at what did I say I'm turning it to? 120 degrees Celsius. So this is the long chain. So from here to here, we now start identifying. From here to here, are we doing heat capacity or specific heat capacity? Why? There's a change in, so this one is specific heat, MC change in theta. What about here? Yeah, okay. of fusion. So we're having latent heat of fusion. What's the formula for latent heat? H is equals to ml. So in this side here, I'll just write mlf. Then what's this side? Of what? That's specific capacity, Abi. MC change in theta. What about here? MLV. And finally, MC change in theta. So the sum of all of them is the heat required to change this thing from here to here. You must always acknowledge the specific heat, latent heat. Are you getting it now? Very good. Very, very good. All right. So at this point now, let's move. Okay, this is an example. Ice at 0 degrees Celsius absorb heat and become water at 0 degrees Celsius. And they give us the latent heat of fusion. This means this is the amount that are needed to melt 1 kilogram of ice. Yes. Next question. So what do we have in that next place now? What do we have? What do we have? What do we have? We've done that already. Next. Heating cup of water. Okay. This is still about latent. Next. That's that thing I drew there. Molecular explanation of melting. Before melting, molecules are closely packed. They vibrate about fixed position during melting. Heat, yes, during melting, heat weakens intermolecular forces. Molecules begin to slide past one another. And after melting, substance become liquid. Next slide. Molecular explanation of boiling. Before boiling, what's happening? That's before boiling, Abi. Then during boiling, what happens? You need to break up the attractive forces between the molecules, right? And what will then happen? The molecules will escape. Yeah. All right. Next slide, please. Calculate the heat required to melt 3 grams of ice. 3 kilograms of ice at 0 degrees Celsius. That's the answer there. ml. Next. That's the answer there too. MV. Okay, let's look at this one. A kilogram, 1 kilogram block of ice at minus 10 degrees Celsius is converted into steam at 100. The total heat required consists of 4 stages. Is this the question that they're helping us? Next, this illustrates what we said already. Practical application of latent heat. Latent heat is applied in refrigerator where we're having change of phase. You understand? Refrigerators, air conditioners, steam engines, thermal power plants, food preservation, ice production, industrial drying process, medical sterilization, using. Yeah. Okay. All right. Thermal conductivity and mode of heat transfer. So, welcome to heat transfer. Heat transfer is the movement of thermal energy from a region of high temperature to a region of what? Low temperature. So, heat transfer continues until thermal equilibrium is established. Right? There are 3 fundamental modes of heat transfers. What are they? So, that's it there, that's the chart. So, thermal conductivity, what's the meaning? Is the ability of materials to conduct heat. And for a material to conduct it, that means it must be a conductor. Right? So, a material with a high thermal conductivity will transfer heat rapidly, while those with low thermal conductivity to transfer heat what? Slowly. Now, thermal conductors and insulators. What are the good conductors? Copper, silver, aluminum, brass, iron. Poor conductors, aka call them insulators. Okay. Okay, semiconductors, like the name implies, you can't place them as conductors because they are not naturally conductors. Neither are they, uh, neither can you just conclude that they are non-conductors, insulators, because that's because until you've pre-treated them, and that pre-treated I'm talking is doping. Until you pre-treated them, you're the one that now decide what you want it to be. Do you understand? The thing there is that there are some of them that when they dope, they actually conduct very well. There are some of them that they dope and conduct well. So that's why it's good. It's safer to call them semiconductors like that. Next. Conduction is the transfer of heat through a material without any bulk movement. Without any bulk movement of the material itself. It occurs mainly in the rear, solids and metals. Energy is transferred by what? So for solid, what you see is vibrations, right? And then there will be free electrons in what? In metals. Okay. Molecular explanation of conductions. Yes. When one end of the metal rod is heated, what will happen? The heat will start getting transmitted via vibration from the proximal end, the part that is close to the heat, to that is further away from the heat, that's the distal end. So molecules at the hot and end, molecules at the hot end vibrate more vigorously. They collide with neighboring molecules, and energy is passed. Yep. So heat reaches the cool end. So in the real sense of conduction, no particle is traveling the entire length of the rod. Only energy. Next slide. So we're looking at Fourier's law. What does Fourier's law of heat conduction state? It's given by Q over T, that is the rate of heat flow, equals to thermal conductivity A. That's the expression the road there is not correct. So we are supposed to have Q all over T equals to Ka change in T divided by L. This is the expression. Well, so that's the correct expression here. So this is known as the Fourier's law of heat conduction. Next. Interpretation of Fourier's law. The rate of heat transfer increases with what? Yes, it also increases with the cross-sectional area, increases with temperature difference, and decreases with what? Length. Please. It's not length, it is thickness. Thickness, because we are utilizing like a block. Do you understand? It's a block. It must be something that has a space. That thing is literally the hindrance for travel. Do you get the hindrance for transmission of that travel? That's of the heat to travel from that one end to another end. Yes? I didn't hear you. Yes. The law states that the rate of heat transfer via conduction is directly proportional to the product of the thermal conductivity, area, and temperature gradients. No, just temperature gradients when you are stating it. All right, so what do we have? A copper rod has those things, those things, those things. You can see 390 watts, right? What's the next thing I'm seeing? Okay, watts, I guess, watt per meter per Kelvin. So calculating the heat transfer, we know what to do on that one. So next, application of conduction. What do you have from there? Okay. What about for insulators? So convection is the transfer of heat through the bulk movement of fluid. Now, pay attention. When we hear the word bulk movement of fluid, we're talking about how the majority of the fluid tend to move in response to changes in heat. How the majority tend to move based on change in heat. Do you get what I'm saying? So, so yes, what really controls that movement is what? Yeah, yeah, I know it's temperature difference, but what controls that convention, that bulk movement of the material, is the changes that occur in their what? No, no, in their densities. You understand? So the more you heat up a material, the hotter a material becomes, the lower its density. So the denser ones, anything that is denser, always want to stay where? No, anything that is denser in always want to stay down in a mixture. You get the denser ones are still cold. So the moment they get heated up to, they will now find their way. They will be lighter than the one up. They will go up. That one that is now up will come down. That's the convection current. Yes, that's what they call convection current. The current, the current has started since the world began, and when you go, when all of us have left this world, to continue. It don't stop. Eh? Because they are close to they are controlled by non-renewable sources of energy. The hotness of the air is due to the sun, except the sun disappear one day. All right. Type of convention, what do we have? Natural convention and forced convention. So when we hear the word, when we hear the word natural convention, those ones occur due to differences in density caused by heating. Remember I said this already? Yeah, yeah. Remember I said it? So what do you have? Sea breeze, land breeze, yeah. All these places, natural convention occurs there. Yes. Calm down. When you're talking about land breeze, it means when you hear breeze, breeze means cold wind. So if they say land breeze, they're telling you that it is the air in the land that is cold. So it's the land air that is going to go and cool the sea. So during what time is the land cold? The night. So land breeze happens in the night. I'm supposed to ask you questions like this. No, no, no. When you go to the sea, night, we'll talk later on. You two will talk. Like, people that are going to sea in night. Okay, let's move on. Oh, yeah. Please go back first. So, first conventions occurs when an external device moves the fluid. like AC, car radiators, water pump, and what? Electric fans. Yeah. Next. Next. So mechanism of conversion. So look at it. Do you agree with me that this is what I've said since? So that's it. That's everything about convection. What is it? What rises, please? Where? No, it's rising means that it goes up. You know what? Air. When you heat up the air, as hot, their density will decrease, so they will find their way up. Lighter things stay up, colder things stay where? Down. Do you understand? Yes. That time when it becomes very noticeable because their temperature, you know now, the heat. Formation of condensation, like when you open. It's like when you open the pot. They're trying to escape now. They're trying to escape that. Yes. Yes. That's Newton's law of cooling. I know you. Yes. Okay, so let's move. Radiation is the transfer of what? Heat by electromagnetic waves, right? Okay, an electromagnetic wave is a radiation, is a wave that, like, there are radiations, I get it, there are radiations that are arranged in order of increasing frequency or wavelength. The mathematical origin of Euler's law is long. Okay, the mathematical origin of Newton's law, the Newton's law of cooling. I'm not talking about it here. Oh. It's not for our class now. It's math. It's for math, applied maths. No, the no. We'll talk about the mathematical formula now. The HA. We'll talk about that one. But there is, you know that Newton's law of cooling originates from applied maths. It's in applied maths, and they used curves and calculus to derive area under a curve to simulate the model. So it takes a maths or engineering students to run through all those derivations, all those that particular derivation. Okay. Radiation is the transfer of heat by what? So please don't write it in your exam anywhere that radiation is when something is getting heated up and because there's no intervening medium and all those things. No, don't do that. Do you understand? Do you understand? Yes. So radiations does not require a what? A material medium, can occur through a what? Vacuum, travels at speed of light. The sun heats the earth primarily by radiation. Do you get that now? Properties of thermal radiation. Hmm? So they're trying to say that those radiations, you know, they are thermal radiations. You can absorb, they can be absorbed, they can be reflected. That means you know, now, just like black body radiations. Yes, no. And any radiation, like when we're discussing radiation, you need to absorb the radiation to feel, you have to absorb the radiation to feel the heat. You understand? You have to absorb the radiation to feel the heat. And sometimes your body might want to reflect the radiation or transmit it depending on the surface. Transmitting means spreading it. So surface properties. Black, dull surface are good what? Absorbers and emitters. But white, shiny surface are what? Poor absorbers and what? Good reflectors. Alright. No. Is it the something, the condensers, something there? Yes. Alright. Comparison of heat transfer modes. Property, convention, radiation. Medium. You want to talk about them in terms of the one that need medium. Does conduction need a medium? Yes. Convection, yes. But radiation does not need a material medium. Occurs in a vacuum. Obviously, it's only for radiation. What's the main mechanism for heat transfer by conduction? Molecular collision, yeah. But for convection, it's about what? Bulk fluid motion. Then what about for radiation? Conduction, yes. Yes, they occur in many speeds. So what are we doing now? Conduction. Heat exchangers, cooking utensils, electronic cooling. So you see, once you can make spoon, you're an engineer. Yes, now they are putting it there so because they want to inhibit that transfer of convection. Then radiation. You can see the application in solar panels, right? Solar panels, infrared heater, satellite thermal control. You see it. Next, thermal expansion of solids and liquids. What is it? Hmm? Oh, okay, move forward. We've done it. That's true. Move forward. So that's like you saw the benefits where they use it. Next, they'll be sweating. But the clothes is absorbing the heat. And it will not transmit it again. Hold on there. Real and apparent expansion. When a liquid is heated inside a container, the real thing that's supposed to happen is that what? Both the container and the water, that is the content, are supposed to expand. Are we getting what I'm saying now? So, so therefore, the observer increase is called apparent expansion, but the true increase is called real expansion. So the real expansion is equal to apparent plus the container. But the real thing that's supposed to happen is that what you are the observer is seeing that only your water is expanding. If you want to calculate your real expansion, we have to calculate the expansion of the container and add it to the expansion of the what? Of that, yes. Yes. Anomalous expansion of water. I think we've discussed that already. Okay. So, what do you now? Another discussion about important. This phenomenon only explains why lake freeze from the top to what? Bottom. Right? So, I've explained this before. Next slide. Denying application of thermal expansion. Next slide. We've done all these things. Next. Next. I'll tell you when to stop. Okay, go to black body concept. Black body concept. The black body is an ideal object that what? Absorbs all incident radiation. It will reflect none, but emit the maximum possible radiation at a given temperature. No. Reflect means you didn't collect it. You bounced away. But emit means you actually collected it and you can still give it back. Reflecting. Reflecting is the bouncing back. No. When I say no reflecting, there is no bouncing back. If it reflects, then it's not a good absorber. If it does not reflect none, it's not a good absorber. Okay. Okay. So actually, I've not noticed that before. I've not. So, emit the maximum possible radiation at a given temperature. No real object is perfectly black, but a cavity with a small hole behaves approximately like one. If any cavity is small hole, including your nose, that's the only thing that is black. That's really black. Nothing is really black. The only thing that's really black I know are my polos. So I think that's that for this. That's that for this lecture. Emissivity and absorptivity. Emissivity is how effective a surface emits radiation. Absorptivity is how effective you absorb. And if you are a perfect absorber, if you are a black body, and you are a perfect emitter and absorber, your value will be equal to 1. Emissivity will be equal to what? 1. So next. Kirchhoff's law of thermal radiation. At thermal equilibrium, good absorbers are good emitters. That's thermal equilibrium. Mathematically, E all over A will now be equals to a constant, where E is emissivity and A is absorptivity. That means you have emitted all you absorbed. So that's it. So you can see the Stefan Boltzmann's law there. That's Stefan Boltzmann's law. This will give emissivity. The other they is a black body. Yes. Next. That's all. So, when do greenhouse effect right here? So, that's that. So, we'll be going for a short break. I believe that people have been listening to the lectures. So we are going to be going to the next aspect. What questions? We have not finished. So the next slide. Okay. So we are going to be doing questions and answer session. We need to solve questions, plenty questions. I think my questions are available. So yes, question and answer time. So listen up. What's supposed to be the next topic there? Calorimetry. Then let me do it because it's supposed to be under this topic. Yeah, so calorimetry, still under the last aspect of what we're doing. Calorimetry. So, right? Calorimetry is an experimental technique that utilizes a calorimeter in determining the specific heat capacity of materials. Determining specific heat capacity of materials. Are we together now? So in this experiment, we are going to be using a calorimeter. I said it there, right? And then let me give you the gist. That's the protocol of how this thing happens before I start demonstrating it on my board. Is it okay? Imagine we have a material of unknown specific capacity and we want to deduce the specific capacity of the material. What do we do? The first thing we are going to do is to heat the material to a very high temperature. You heat the material to what? Very high temperature. The most important thing in calorimetry is recording. Is what? Is recording. That's the most important thing, recording. What do we do? Thank you. And when we heat it to a high temperature, we record its temperature. Right? We even leave it heating. We will get water in a calorimeter. And now what would we do? We'll record the temperature of the water and the calorimeter. Are you getting me now? Then we will now introduce what? The heated, the temperature of the water and the calorimeter and the water, they will equilibrate. Yes, they will have to because they've been in contact for a period of time. Yes, they will have to they will equilibrate. So we will heat the material and then we will introduce the material into the water and stir it. The moment we introduce the material into the the moment we introduce the material into the water, it becomes a mixture. It becomes a what? A mixture. So anytime in the experiment you use the word mixture, I get me now. It means we're talking about when we put the hot ball into the water. So the mixture is when you have the hot water, the water in the calorimeter. That's the mixture. Theta M. You need to record everything you have. Oh, we need the measurement of all the masses. Because we're going to use the formula MC change the theta. So everything must be recorded. Are you following what I'm saying? I didn't get you. The first temperature you measured, that's your initial temperature of water and calorimeter because they have the same temperature. They will experience the same temperature change because they are in thermal equilibrium from the beginning of the experiment. Eh? Yes? You know this thing you're asking me now. Okay. So what's next? I'm not clumsy. So we're going to be demonstrating it. Now, in our demonstration, please can you help me with the projector or fix it somewhere else? Okay. So yes. So yes. Let this be a bouncing burner. And let this be the ball of unknown specific heat capacity. Listen to me. Let this be the ball of unknown specific heat capacity. C is unknown. Are we together? The C is unknown. We know the mass, Abi, and that's what we know for now. So we are heating it up. While we are doing that, we'll get a calorimeter and pour water into it and stir it so that they can equilibrate quick. So when we do that, we must, before we even put the water, we have measured the mass of the calorimeter. There's a stirrer on the copper calorimeter. There's a stirrer on the copper calorimeter. Yes. So that means both of you have not seen a calorimeter. Eh? I don't have what am I using. So MW, MC and MW. What is MW? Mass of water, right? MC is what? Mass of calorimeter. So when you have heated it, you have measured the temperature, we can call the temperature theta 1. I get me now? We can call it theta what? 1. Then, the moment we remove this ball, the first thing we are doing when we are removing this ball is that we are measuring its temperature. We are doing what? When we measure the temperature of this ball, we record that temperature of the ball. We can measure it theta 2. Immediately you remove it, you drop it inside the water. You drop it inside the water and do what? And you stir. Now it is a mixture. So when we've stirred it and it equilibrates, can you hear me? What are we going to record? That means the final temperature of the water the ball and the calorimeter is theta m. Theta what? So we'll call this one theta m, which is the temperature of mixture. It's the same way, it's the same thing as saying final temperature. I get what I'm saying? The same way as saying final temperature. Yeah. All together. So we'll come here and start doing our recordings. So the question there is, when we introduce this hot ball into this water, what happened? The hot ball will start losing its heat energy to the water, right? Why the water will start gaining that heat energy, right? So it's very easy for me to call it. It's very easy for me to say heat lost by who equals to heat gain is equal to heat gain by who? By water and that's plus calorimeter. Yes. So therefore, what do we now have? Bounce calculate heat lost by ball. I'm saying m of the ball, c of the ball, which is what we need, Abby. Change the temperature of the ball now is what? Theta 1 minus theta m. So just make this one the subject formula. MCC m minus theta 2. All right. Yeah. Yeah, so it's a solid. If it's a liquid, you put a solid, a specific heat capacity. Yes. Do you understand that kind of thing? It's not the liquid you'll be looking for, is all. So yes. Yes. So let's do that. All right. So let's do some questions. Okay. So we're going to be solving a number of questions. Going to be solving questions. Okay, let's run. Can I adjust the parameter? A steel tape measures the length of a copper rod as 90.00 centimeter. A steel tape, a steel tape, a steel tape measures the length of a copper rod as 90 centimeter when both are at 10 degrees Celsius. When both of them are at 10 degrees Celsius. And the calibration temperature for the tape, full stop. Yeah. And what would the tape read for the length of the rod when both are at 30 degrees Celsius? Uh, yes, you can. They gave the linear cap. They gave the linear, the specific, the one for steel. Yes. I think it's the typographical units. Yeah, I'm waiting for you. I don't understand. Wait, maybe it's my. Which one I gave you? I said, what will be the length? I said, I said, what would the tape read the length of the rod when both are at 30 degrees Celsius? How did you get the answer when you don't know the linear expansivity of steel? Where do you know the temperature of steel? Network, hotspot. Sure. Next question. Yeah, I'm looking for this. When a building is constructed at minus 10 degrees Celsius, a steel beam with cross-sectional area 45 centimeters square is put in place with its ends cemented in pillars. Is put in place with its ends cemented in pillars. With pillar, with its ends cemented with pillars. What if the sealed ends cannot move? If the sealed end cannot move, what will be the compressional force? What will be the compressional force on the beam when the temperature is 25 degrees Celsius? Huh? I don't hear you. 25 degrees Celsius. Alpha is equal to alpha is equal to 1.1 times 10 to the power minus 5. And gamma is equal to gamma is equal to 2 times 10 to the power 11. Yes. Same. Correct. Then, next. Yeah. They give you a question that is no parameter. For which thing? Meter. Because of the. Mm. So, so I want to give us questions in temperature. Right. A stainless steel. A stainless steel wire is 150 centimeter long. Is what? 150 centimeter long at 20 Celsius. An electric current is passed along it and it expands to 151.2 centimeter. An electric current is passed along it and it expands to 151.2 centimeter. 151.2 centimeter. What is its new temperature? I'm coming to give you. Yes, specificity of all. Which is that one? Which one do you need? Of which material? 3, 3, 36 times 10 power of minus 6. 10 raised power of minus 6. There are different kind of steel. There's stainless steel, there's structural steel. The one I give you is this thing. Is it this? Yeah. I'm coming. Yeah. I'm waiting for them to solve. What do you get? Correct. Number 3. It's still tip, but you know. The density of mercury. Density of mercury. The density of mercury at exactly 0 degrees Celsius is 13,600 kilogram per meter cube. The density of mercury at exactly 0 degrees Celsius is 13,600 kilogram per meter cube, and its volume expansion coefficient is 1.2, 1.82, 1.82 times 10 raised to the power of minus 4 per degree Celsius. Per degree Celsius. Calculate the density of mercury. Calculate the density of mercury at 50 degrees Celsius. Thank you. Okay, I think I've gotten the answers now. Isn't that the one? Right. Next question. Is anything incorrect? Oh, yeah. Yeah, no, next question. How much water will flow in 30.0 seconds through 200 milliliter capillary? How much water will flow? How much water will flow in 30 seconds through 200 milliliter of capillary tube? How much water will flow in 30 seconds through 200 milliliter of capillary tube? 200 through 200, like via 200, but through, like pass through 200 millimeter of capillary tube of 1.5 millimeter. If the pressure differential across the tube, if the pressure differential across the tube is 5, if the pressure differential across the tube is 5, is 5.0 centimeter of mercury, the viscosity of water is 0.801 cp, and rho for mercury is 0.801. The viscosity of water is 0.801 cp, and P for mercury is 13,600 kilogram per meter cube. Huh? That's all. So what are you guys getting now? Yeah? Coiselus. Alright. Are we good? So we're using your Poisson equation. You're going to be utilizing J equals to pi R4 open brackets change in pressure divided by 8 viscosity. What is it? Yes. All right, so what volume of water? What volume of water will escape per minute from an open top? From an open top tank through an opening 2 centimeter. Through an opening 3 centimeter in diameter. That is 5 meters below the water level. That is 5 meters below the water level in the tank. That is 5 meters below. That is 5. Not at 5. That is, hey, yes, that is 5. Above the, sorry, that is 5 meters below the water level in the tank. That's all. Eh? You drew this diagram I'm drawing. This diagram. Water is inside. Eh? You didn't give. Ah. You do. Like which law? Brazilian law can work. So what are you doing? What are you using? You need help? Do you need help to reset the equation? You will eventually do that, but you have to use to refer the solid first. You have to use to reserve it first. Eh? The 2 square root 2 g stuff. That's 2 gh. So how are we doing? Can we get it? Be fast, get it. You know you will get it. Thank you, yes. What did they ask you for? What did they ask you for? For volume what? Where you need to write the question. What volume of water will escape per minute? So what are they asking you for? Eh? Yes, now just convert. When you are done, convert everything to convert it to per minute. Sure is there no volume? Why is there no volume in continuity? There's volume. Uh, is J, but is flow rate not equal to is flow rate not equal to AV? All right. Huh? Yes. So area area in the formula is cross-sectional area. Yes. What is it? Yeah, correct. Yeah. I'm coming. All right. Yeah. So I'm trying to sort it. A thermos flask contain 250 gram of coffee. 250 gram at 90 degrees Celsius. Are you there? So this is added 20 gram of milk. So this is added 20 gram of milk. At 5 degrees Celsius, full stop. 20 gram of milk at 5 degrees Celsius. Full stop. After equilibrium is established, what is the temperature of the liquid? Assume no heat loss to the thermos bottle. Eh? The Is it ready? Is that one ready? What happened? It's not ready. Is that ready? My ID come. Is it ready? Beating. BRMS. VRMS. 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 Let's put it. I didn't hear you. Is it what? Yes. Okay. Okay. So we have a thermos, so you got 83 something. Sure. That's the first one, and then you go against it. In a calorimeter can. In a calorimeter can. At 200 grams of water and 50 grams of ice, all at exactly 0 degrees Celsius. Yes. All at exactly 0 degrees Celsius. Into this is poured 30 grams of water at 90 degrees Celsius. What will be the final condition of the system? Of the system, yes. What will be the final condition of the system? What? They tell you to calculate this, the mass. Solving this equation yields. You will find out what you are looking for. Is the mass. The mass of the ice that melted. The mass of the ice that melted. It's not all the ice that will melt. Yes, that will give you the amount of ice that melted. So, longer module 14. Ideal gas lecture. I think just continue solving, continue solving. Let me give you an hour. Yes. Eh? What's the question again? It's not, oh, it's not. Eh? Almost. Fine, let's go there. Let's go there. A 3-gram bullet. A 3-gram bullet. Open bracket. A 3-gram bullet. Open bracket. Open bracket. C is equal to 0.0305. Yes. Sorry. Sorry. Cancel it. Just that's 0. C is equal to 128 joules per kilogram degree Celsius. Moving at 180 meters per second. Moving at 180 meters per second. Enters a bag of sand and stop. Now, what amount does the temperature of the bullet change if all its kinetic energy becomes thermal energy? Should I come again? A 300-gram bullet of specific heat capacity 128. A 3-gram bullet, 3 gram, 3-gram bullet of specific heat capacity 128. Moving at 180 meters per second. Enters a bag of sand and stops. By what amount does the temperature of the bullet change if all its kinetic energy becomes thermal energy that is added to the bullet? Okay. So, are you done? What are we doing? What have we got into? What's the plan? What's your solving plan? Yes, 1 to 6.56. I don't know. One on the okay, let me an iron plate 2 centimeter thick. An iron plate 2 centimeter thick has a cross sectional area of 5,000 centimeters square. Full stop. One face is at 150 degrees Celsius. One face is at 150 degrees Celsius, and the other is at 140 degrees Celsius. How much heat passes through the plate each second? How much heat passes through the plate each second? For iron, KT is equals to 80 watts per meter dot Kelvin. What value are you calling? Yeah, 20,000. Sure. You guys are you people sitting down together in Japan? Because that's the worst combo. Jesus. Yeah. Oh, yeah, yeah. Oh, yeah. Calculate the R value. R value. R value for a wall consisting of the following. Calculate the R value. Oh, God. An error question, sorry. About what? That's the line that side. So hold on as I bring what's in my mind. Okay. Let's go. A a string 2.0 meter long, is driven by a 240 hertz vibrator. It's driven by a 240 hertz vibrator. 240 hertz. A string. How does that look? I pity you. I pity you. It's supposed to be an innocent child. A string 2.0 meter long is driven by a 240 hertz vibrator at its end. The string resonates in 4 segments, forming a standing wave pattern. What would be the speed of a transverse wave on such a string? A string 202 meter long is driven by a 240 hertz vibrator at its end. The string resonates in 4 segments, forming a standing wave pattern. What would be the speed of a transverse wave on such a string? I'm looking for the question. Where is this thing now? Anybody knows the right question? I've seen it. What's the answer? 0.24 kilometer. All right. What sound intensity? What sound intensity? What sound intensity is 3 decibel louder than the sound intensity of 10 Weber, 10 microweber per centimeter square? Have you seen the question? is 3 decibel louder than the sound of intensity of 10 microweber per centimeter square. 10 microweber per centimeter square. Number 4. Opposite. I not. I not over. Yes. I not equals to I bracket. This one, yes. Yes, yes. Remember. Sharp. Please tell it. I. Please say I not. You talk I not. Now, formula like that. I not. Right. You can write it in different ways. There's different ways you can do it. Right. Just leave it. You can use logarithmic form. You can use the normal form. Then you can use link. 10 log open brackets I over I naught. That's what is equals to sound intensity level. The I is the sound intensity level. You're looking for the. What did the question? Did the question give you the decibel? Okay. No mistake, that's it. Okay, let me bring that jog. Okay, let me bring that jog. I said, you help me bring that jog. The drug. All right. So are you done now? Are you done? What's your answers? Why don't I use this thing now? Have you solved it? Yeah. Have you gotten it? Have you gotten it? What's your B? What's the B? The B is what? 3. From where? How? So we got 3 times 10 raised to the power minus 4. It's not answer Aisha. I just realized it's from exercise. It's from the exercise of shams. What is it? Should be they give how many this one? What's the other one decimal? Sound decimal. Which sound decimal did they give us? 10 microweber. 10 microweber per centimeter. That's also intensity. 10 Abi. That's intensity now. So what do you have? So there is which mean sound intensity. I don't want the sound intensity level. There are the 2 sound intensities now. There are the 2 sound intensity level. So now I have 10 raised to the power minus 3. I'm going to 10 raised to the power 1. I2 is now equals to what? Done. That question, okay. Wait. Drop it there. Drop it there. Drop it there. All right. Yes. So, hmm, I would have loved to go to the next topic tomorrow, but so small face. All right, now we are moving into another session, module 14, as we will be tracking up on ideal gases. Let the lecture begin, sorry. Foundations of gases. So, yeah. So we want to first of all run through an overview as to what gases really are. So what are gases? No, I'll tell you myself. What are gases? Gases are one of the three fundamental states of matter. Are we together? Please pay attention. Understanding their basic nature and measurable properties is first step to studying gas laws and videos. So yes, they all have unique properties and all, and we make use of microscopic variables such as pressure, volume, and temperature to study them. Standard reference conditions are STP, NTP, SATP, right? And are used for comparison and gas calculation. What's the meaning of STP? Okay, NTP. Yes, what NTP? Mm. Well, that's what, as a rule, you know, so that's what I'm saying. What's the meaning of SAT is saturated temperature? Yes. What was NTP? No? Yes. That is when the temperature is the old name for room temperature. All right. So, yes. So, definition of gases. Is it possible to zoom and make this thing wider? Definition of gases. A gas is a state of matter in which the constant particles are widely separated and move freely and randomly in all directions. You see that? So, that's the gas. They move freely and randomly in all directions. So, gases basically don't have a fixed shape. They have no fixed shape. They have no fixed volume. So when you say they have no fixed volume, it means they can expand and fill the entire container. That's one major characteristic of a gas. Yes, no, they can expand on their own. Yes, take this over the container. Basically, yes. They will spread out. They will spread out. You understand? Yeah. Yes, no. Yes, that's one of the five postulates. As now, no. So ideal gas, for ideal. So let's go. So they're highly compressible because they are gases. They have low densities compared to solids, and their particles move rapidly and randomly. Yes. Next slide. Characteristics of gases. Gases, they have no definite shape or what? Or volume. And that's very true. In what sense is it true? Okay? So they expand to fill any container. They are easily compressible. They exert pressure on the walls of the container. How? By collision. So the more the rate of collision is existing the uh, between the molecule of the gases themselves and the walls of their container, the higher the pressure within the system. Yeah, they are perfectly elastic based on the fact that they collapse themselves and separate. Right. This one. So if what gases flow easily. Gases, yes, that's part of diffusion. So yeah. Oh, yes, they can easily diffuse. We use the word diffuse, yeah. So right now we have solid, we have liquid, we have gases. So volume, in terms of volume, solid have definite volumes, right? And liquid have what? They also have definite volume. And then gases have no definite volume. I mean, so in terms of particle spacing, what do we have? They're far apart. Okay. In terms of intermolecular forces, what do we have? For which one? Yes. Well, they have a very high degree of freedom. And okay. So in terms of density, solid they have what? High density. Liquids have moderate density, and gases have very low density. Then mobility of these ones they vibrate about their position, slide um, around one another. The other one move freely. All right, next. So gas particles are in constant random motion. They are separated by large distances, much larger than their sizes. The intermolecular force between gas particles and negligible. Collisions between particles are elastic. There is no loss of kinetic energy. Particles move in a straight line until they collide with one another particle. or the wall of the container. That's one part of gases that many people don't appreciate. They don't understand. For them to tell you that gas moves in straight line. That means if you have one atom, one molecule of gas here, it's going to continue going in a straight side without changing direction until it collides with something else. Multiple collisions are going on. If not, that would be the most organized transit to heaven. The thing just anyone that face sky, you reach. Eh? Which thing? Which thing? Which trapped? Okay, so what will happen? How will they move? Okay. Oh, yes. So next slide. Microscopic properties of gas. The behavior of gas can be described using measurable properties. And we have them here. Pressure, force exerted per unit area by gas molecule in the wall of the container. We have volume, which is the space occupied by the gas. Temperature, measure of the average kinetic energy of the gas. Yes. Yeah. Yeah. So these properties are interrelated and form the basis for studying gas laws. Next, pressure, volume, and temperature concept. Pressure caused by collision of gas with wall. Okay. Okay. Next. Next. Standard reference condition. Oh, normal. Yeah. Then we have standard temperature and pressure. Please keep the value in your head. So which one is not the room? Okay, it is this one that is the room. Okay, move. Next. Property of gas. No. Yeah, that's what is there, yes. That is what the case will be. Property of a gas. Oh, yeah, what are the properties of gas? We have this thing has appeared 4 times. This next. 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 Okay. Slide back. So, all my plans. The empirical laws. The empirical laws that controls the behavior of the gas. So they describe, yeah? Yes. Yeah, those are the gas laws. So, um, while we review this slide, we'll continue with question. So, James, let me tell like this, the thing is bringing out pressure. bringing out information for chemistry kind of concepts. And that's what the thing is bringing. Okay. All right. So the charges represented in the diagram below are held stationary in a vacuum. Find the force. Find the force on the 4 microcoulomb charge. On the 4 microcoulomb charge due to the order 2. So I'll be answering it so that we can use it, and then let me just start. You're not around when we did electrostatics. And I remember you asking me that when am I going to do it? Right? So I'll use this question to explain it to you once and for all. You ask me again. So, right. The charges. Okay, no, don't worry, we'll do it another time. We'll do it another time. So it was type ideal gas, kinetic molecular theory of gas. Which one? Column. It was electrostatic. Right. How much work is done? How much work is done? How much work is done by regas in expanding isothermally from an initial volume? From an initial volume of 3 liters at 20 atm to the final volume of 24 liters. At 20 atm at so final volume of 24 liters. Final volume of 24 liters. How much work is done? in expanding isothermally. Where are we? So you're going to be applying is what? 4? No? No? It's isothermal expansion now. Change the W is equal to P1V1 lane. No. No molar diffusion. It's not adiabatic. Isothermal. Isothermal. That is the P1V1 lane, open bracket, V2 over V1. Yeah. Approaching this kind of question, you say work done is equals to, yes, P1 V1 lane V2 over V1. Because that's not isothermal. Yeah? No. 12.6. What was the answer again? Then I get 12.6, or you're getting, that's 12.6 is a kilojoules. You're getting 12,600. So yes, the next question. Very soon now, to be on 50. Oh, yeah, I don't know. Isothermal. Like ordinary PHHV. That's work done in the gas. It's not in the thermodynamic system. 20 cubic meter of monoatomic gas. 20 cubic meter. of monatomic gas and 100 kilopascal is suddenly, in brackets, is suddenly, open bracket, and adiabatically close the bracket, close, compressed to 0.5 centimeter cube. Stop. Assume that we are dealing with an ideal gas. What are its new pressure and temperature? Are we good? Are we good? So, what are the values? Sorry, please come again, please. Yeah. Yeah. Yes. Uh-huh. Thank you. So what are we having now? What are we getting? This is under thermodynamics. And the the whole thing would have been easier if they did not write adiabatic there. So with adiabatic there, and the fact that they even did the honors, did you the honors. Sorry, they gave you guys the YO. Yes. Are you calculating it? Sorry. 1.67. 1.67. Sorry, so sorry. So what are we doing? Since you've been solving that question, since do I just solve it? All right. You got what? 2.89. 4 points. That's for which one? 4.5 times 10 power what? 12. Well, there's a mistake somewhere. What's it? 47. 4.74 times 10 to the power of 7. What do you use as your P1? How? You can use kilopascal. You convert to Pascal. Very brilliant. That's great. That's great. Find change in W. Yes. Find change in W and change in U. for a 60 centimeter cube of iron. For a 60 centimeter cube of iron, as it is heated from 20 degrees Celsius to 300 degrees Celsius at atmospheric pressure. For iron, C is equals to 0.11 cal per gram per degree Celsius. This specific heat capacity. You what? Iron, for iron, C is equal to 0.11 cal per gram per degree Celsius. There's thermodynamics. As we just treated it, was still there. Thermodynamics. No. And the volume coefficient of the expansion is 3 points. 3.6. Yes. Yes. 3.6 times 10 power minus 5. Oh, all right. Anyway, all right. Yeah. So, let me see what you're doing. Okay, yeah. Good. And I'll do it. Work on it, work on it. That's part of our class activity for today. We have 4 class activities. Time is going, please. Work on it. Okay. No, I can't give you options. Please be fast. Thank you. How do you 100 three times? Whatever 100 three times gives you, that's what. Like you divide by 100 raised to the power of 3. All right. Since you have 1 more minute so that we can get on to another question. Okay, let's say 2 more minutes. All right. The work done. The work done. Yes. What are we having there? So we're having work done is what? Work done is what, please? All right. So are we done now? Are we done? All right. All right. Huh? No. Did you write the question? No. Okay. Just hold on. Let me just take 1 minute break. 1 minute break. Recording. I'm supposed to have 10 minutes, guys. All right. Where's the seafood? All right, so have you finished? Have you guys finished? Have you guys finished? So, all right, so yes. Find change in W and change in U for a 6 centimeter cube of iron as designated from 20 centimeter. So, change in W. Now, given that change in T was what? 300 minus 20, right? Then we can easily use H equals to MC change in theta. Did you guys do that? There's no mass. Where did I read your question to? In your notes, you now have and the volume coefficient of thermal expansion. The mass of the cube is 1,700 grams. So I think that solves your problem now. Listen. What's that? The what? Up to it. You can also check other parameters as well. That's really parameter there. So you can do it like that. Yes. Alright, so what's the plan? Yes. Alright, so how are we doing? So what steps are we taking? The values for the you've gotten the linear specificity part as a work. So what's the parameter? Help me with the values. I need numerical data. Yes. Okay, I'm out of that one. The so on the same page. Answer this question. Thank you. That's for which one? Changing. For which one? No, people are not correct. 5 points what? Omo, omo. Are you working in kilocal or joule? Normal calories like this. Oh yeah. See that MC change in theta. What does it give you? I tell you the one will give you 52. Oh, you're not giving him 52. I don't know, but I just feel. Let's always do it. I don't know, I feel the error is coming from your end. So. But nevertheless, we'll do the correction now. So let's work on the correction. So here, we're giving and made to understand that so here T Change in temperature. Change in temperature is equal to, what do we have on that? 300 minus 20. That gives us what? 280. We're having 280 degree Celsius. Now, we'll get the specific heat capacity formula. We have change in Q is equal to MC change in what? Theta. Okay? Okay? So they give us the mass 1700. That's okay. So we have that the change in Q is equal to what? So I'm writing 7. She means is calories. It's not calories. So we're working with gram. Just leave everything in gram like that. Because calorie per gram they are writing there. It's gram. So we have 1700 open brackets 0.11 multiplied by what? 280. If the people attending secondary primary school, you will not be having problem with these things. So what do you have? Like that. Yes. 52 what? All right. Minus. That's the first part. Yes. So you say you should for waiting. What you ask yourself now is this simple question. How do you calculate the work done? Say what? P change in V. How do you get your change in V? Say, so W is equals to P change in V. What did you get? As what? As work done. As work done. That's your own work done. So here now, what was the volume of the cube? Okay. What was the volume of the cube? Volume of the cube. Now, for the fact that we are pursuing joules, you dare not think you use calories and be getting joules, right? Or is that what you've been doing? You didn't change it. But you have gotten work. So your work was in what unit? Convert your work to joules for me. Oh, the hour has been waiting for. It remain hundreds. It may have remain 100 again. You mean that's 9. 4 points. So you're converting from what? How? Is calories a unit of work? Is calories a unit of work? Eh? Because joules is Newton second, not calorie anything. What's this? Okay. So when you were getting the volume of your cube as a centimeter cube, did you change it? So what did they give you now? Which one is V2? You're changing V. Six. I will put calculating it. To determine the volume of the cube, we already know that V, change in V over V is equal to what? B change it. Am I correct? Better now. Is it supposed to be gamma? Okay, gamma. Are we together? So the volume V is 6.0. When we square it, we get 2.16. That's with qubits. They didn't give us the volume in that question. I'm not settled now. I'm not settled now to audit it. I'm not settled down to be able to check it. When it comes in. Let's go. Now, you're talking now. What's the unit? Sharp. Next question. A 2 centimeter, a 2 centimeter thick brass, a 2 centimeter thick brass plate, open brackets, KT equals 1/5. KT equals 1/5. Yes, 1/5. Yes. Watt per Kelvin dot meters is sealed face to face to a glass sheet. To a glass sheet. Open bracket. KT equals 0.8. Glass sheet. Open bracket. KT equals 0.8. Watt per Kelvin dot meters. Close bracket. And both have the same area. Full stop. The exposed face of the glass plate. The exposed face of the glass plate is at 80 degrees Celsius. The exposed plate of the glass plate. Yes. Why the exposed face? You know, the one I said, the exposed face of the brass plate is at 80. So, why the exposed face of the glass is at 20 degrees Celsius? (20 centimeters), 20 degrees Celsius. How thick is the glass? If the brass, sorry, how thick is the glass? If the glass brass interface is at 65 degrees Celsius. How thick is the glass? If the glass brass interface is at 65 degrees Celsius. What is it? I should count it for you. There are three in number. We have an 80 degrees Celsius here, we have a 20 degrees Celsius here, we have a 65 degrees Celsius here. There is, I didn't say it's 90 degrees. All we are having there is 80 degrees, we have 20 degrees, and 65 degrees. All right, I'll be waiting for you guys to solve that question so that I can analyze it with you if you don't get it. must keep quiet for 30 seconds. I don't understand. Something I'm check. What are you saying? Yeah, where is Sam? I can even keep quiet for 2 hours, seeing as much as I'm watching. So, but nevertheless, one thing about physics is it's better you take the safer steps in physics. Seriously. So our voice shall be heard. Where are we? Have you solved it? Please solve it. Please solve it. What are the parameters you are using? Give us data. 0.0045. Okay, that's correct. Next one. Next one. Wait, sit down first. Please, the regulators should be called. They almost left the class together. You'll be empty. So the next question. Suppose when, okay, wait. Question is, what temperature gradient must exist in an aluminum rod for it to transmit 8 calories per second? All right, we are solving questions at the moment. We are solving questions. So you attend the questions and tell us your answer so that we can just move. Yes. So yes, we'll start from here. The kinetic theory of gas. You see that? Kinetic theory of gas. The kinetic theory of gas, the kinetic theory explains the behavior of gases in terms of the what? Motion of tiny particle molecules and the force acting on them. Now, the key takeaway is that what? Gases consist of tiny particles in constant motion. Their collision produces what? Pressure. You see that? Their collision produces what? Pressure. Do you understand what I'm saying? And temperature. The theory helps us understand and derive gas laws, and it forms the foundation of thermodynamics and statistical mechanics. Okay? Assumptions of the kinetic theory. The kinetic theory of gas is based on the following ideal assumptions. Now look at the assumptions. First assumption, a gas consists of a very large number of tiny particles that we call molecule. Do you understand? So every gas you see, the simplest basic unit of the gas, we call it a molecule. I get what I'm saying? Now, the actual volume of the gas molecule is negligible compared to its volume of the container. So, for the fact that gas molecules are small compared to their container where they are, is what makes us conclude that the volume of the gas is going to be usually reported as the volume of the empty space. You know about that before now? All right. There are no intermolecular forces between these gas molecules. There are no intermolecular forces between these gas molecules. And then collisions between molecules and with the wall of containers are perfectly elastic. And finally, the average kinetic energy of the molecules is directly proportional to to the absolute temperature. That last statement links up to this. It links up to this. Average kinetic energy is proportional to what? Temperature. Is that what they said? Now, when you want to remove this, you bring in your constant, Abi, and I have this. That constant I'm bringing in is actually I follow you. Now, there is another constant that we are going to bring here. Are you with me? There's another constant that we're going to bring. And do you know the name of that constant? We call that constant K. Let me keep the space out. The constant is 2 over 3 kBT. Are you with me? Now, this thing can be opened. Average kinetic energy is 1 over 2 mv squared, which is equal to 2 over 3 kBT. Are we together? Okay. So, sorry, I wrote 2 over, it's 3 over 2. 3 over 2, please. This can cancel this, Abi. What do you now have? mv squared equals to 3 kBT. Make it the formula. What do we have? You understand what I'm doing now? So at this point in time, you can now do what? Normal. This KB, you can turn it to R. KB can be turned to R. So if you turn it to R, this one here will not be small letter M, it will be capital letter M. So we'll be having so we're going to be solving questions on the VRMS using this formula. You understand? So I can sync. And the R, because we are looking for this, the R is, we have two possible values of R. We have the 0.0821 that they use in gas laws. But this is physics. So we are doing more of energy. This thing now is an energy linking stuff. So we make use of 8.314 for our universal gas constant. Are you with me? Very good. You are writing, Abi. You are not writing. Why are you in a hurry? Write carefully. We have all the time in the world to make sure you learn. I get what I'm saying. That's what the time was mentioning then. So, all right. Are you awake? Are you awake? No, listen up. Listen up. There is about one hydrogen atom per cm cube. There is about one hydrogen atom per cm cube in our outer space. There is about one hydrogen atom per centimeter cube in the outer space, where the temperature is about 3.5 K. 3.5 Kelvin, that's K. Have you finished? Where are you now? So find the RMS speed of these atoms and the pressure they exert. Have you started solving it? What are you doing? Find the RMS speed. This is RMS speed. What is this? I guess this is RMS speed. Find the RMS speed. Find the RMS speed of this atom and the pressure they exert. This is a piece now. They have solved it. Let me see how it works. How did you do it? Hmm? Answer is what? So what will happen now is what will happen now is right square root 3 times square root 3. Write it now. No, we are writing a calculator. Square root 3 times 3.14. Mm-hmm. Then that's not all. So we have done, have you put the temperature? Yes, times 3.5. All over the mass. What do you put as mass? Is it if it's for our choir is easy? So, I'm looking for the question. All right. So, what do you get now? 5.7, no? What do you use as your molecular mass? -1. More like you are getting, when you're using 1, it would have gotten you qualified. What is it? It was supposed to be 2. That your under. Maybe it's hydrogen gas. Make it 2. Like, 1 hydrogen gas contains 2 hydrogen. Well, like hydrogen gas contains 2 hydrogen molecules. So you can just use 2. Like, put hydrogen mass inside. 1 as totally 2. And you need them. No. You will get your answer. I guess. Run again. Have you gotten it? 4. That's enough. And average I'm seeing there is more. What is it? 84. Your denominator. I already told you what to use right now. Disturb me. No. Which one? Okay. What's 2? Yes. Bring it. Bring it, let me see. So, where is it? What are the parameters? 3. What do you put in them? Why we don't see my R? No, you divide your picture by something. You get your picture. You have it. Sorry. What is it? Let me see your work so I can press it.
Is it plus or times? You put it at
Times. So hold on. So go and press it. This 3.5 is for what? Okay. As I mean, why this one come? As I mean, be pressing it.
from 6.6.
I'm zeros for me, don't worry. I'm correct. Okay. I'll be happy if you work as well. This one. I'm saying something now. Okay. Yes. All right. Okay. 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 So you now, you've gotten the answer, have you?
No.
Write this question down. You're in that dimensional analysis class. You're in vectors too. Write it down. Yes, very, very. Where was this idea since? When my year one come out? So, all right. So, write this question down. Try out for you. A car's odometer. So find the range. Find the range X of a gun that fires a shell with muzzle velocity V. Find the range X of a gun. Find the range X of a gun that fires a shell with muzzle velocity. Where do you write last? Where are you? Okay. What is it? What do you write last? V at an angle of elevation theta. So, are you working on it? Let me see the question. As the temperature is temperature of 5 kilo. So now let me chop these farms. No come like now let me chop these farms. Finish fast. Okay, are you done? So I believe you now understand anything that has to do with velocity and root mean square. Very good. Very good. So I watch you. Maybe that's one that you're trying to do. Let's see how it goes. I saw your work. The work looks complete 100%. And do it this way. So have something like this. 3 times R 8.314 multiplied by 5 3.5. I mean the time uh, divided by everything in the middle. Do this one. Calculate the root mean square speed of an oxygen. Calculate the root mean square speed. The root mean square speed of an oxygen molecule at room temperature. Done. Let it stop. What did I say? Like, Uh-huh. That's all. Just the open bracket. Take that should be 23 degrees Celsius. All right. So when you saw me, what do you get? I think 25.08. Call the question for me. Let me see. Mm-hmm. Take what? Okay. R. Temperature is what? Yeah. Divided by what? Divided by what? Divided by 2. So that gives us what? What does it give us? 16. 60.75. Let's calculate. Let's do another one. Determine the kinetic energy. Determine the kinetic energy. Determine the kinetic energy in 1 mole of any gas at a temperature of 300 Kelvin. Determine the kinetic energy in 1 mole of any gas at temperature 300 Kelvin. At temperature 300 Kelvin, first of all. Notice that the total kinetic energy is independent of the type. Notice that the total kinetic energy is independent of the type of molecule, as long as it behaves as eh? I'm waiting for you. No, read your question. I've read the kinetic energy, so where is it? Okay. All right, so what are you getting? Yes. KB is the constant. 1.38 times 10 raised power minus 23. 1.38 times 10 raised power minus 23. 1.38 times 10 raised power minus 23. Okay. I still on it. But what the parameter? They give you the temperature.
Yes, 300.
What is it for kinetic energy?
Yes.
6. Fine. 6.2. Okay, good. So what do you know now? Okay, we should another one. Write another one is an expression. Leave that one. Calculate the root mean squared velocity. So the root mean squared speed of carbon dioxide molecule. Root means the speed of carbon dioxide molecule. Calculate the root mean square, the RMS speed of carbon dioxide molecule at a temperature of 310 Kelvin. At a temperature of 307 Kelvin. Assuming they behave as an ideal gas, assuming they behave as an ideal gas, hold on. Hello. What's the value? What? It's 1 mole, but you have to get this in a molar. It's the molar mass that's waiting there. Hello. 4 points. You call the parameters for me. What did you use? You use this formula here, right? This one, Abi. Which one do you use? Okay. They asked you for the VRMS, Abi. So what did you? What was the carbon dioxide? 18 watts. You cannot use that 18 no. 18 gram per mole, Abi. You have to turn this 18 to kilogram. So that's 0.018. That's what I'm going to use. So you should also correct the previous ones. That previous one you did. You get? You don't? For the carbon dioxide. What is it? Is it the carbon dioxide? Like, I'm asking, is it the carbon dioxide we did? That's the one. What? Which question are you talking about? Of CO2. Oh, that's a local problem. Hmm? I'm coming. Let me just do it myself. It's going to be square root of what? Huh? 8 point what? Have you pressed it to your calculator? Press it, press it, press it. That's what you got. Then you're correct. Done? Okay. Let's do more. what molecule, what temperature, what temperature, what temperature will the molecule of an ideal gas have? At what temperature will the molecule of an ideal gas have twice the RMS? At what temperature will the molecule of an ideal gas have twice the RMS speed they have at 20 degrees Celsius? At what temperature will the molecule of an ideal gas have twice the RMS speed they have at 20 degrees Celsius? Did you hear the question well? Yes, yes. Hmm? Wow. So look at this. What do you have? Check. No, just read out the question for me. With the what? What? What's the question? Start again. With the molecule of an ideal gas. Okay. At what temperature? So the question is at what temperature will the molecule of an ideal gas have what? So let's take this one as T1. What's its RMS here? We don't know, we'll just call it R1, Abi. So we're looking for the temperature where R2 will be equal to what? 2 times of R1, Abi. So let's pick out only these two things. We're only going to be picking out these two. So from here, what do we have? Have T. We are using this relationship. Velocity is directly proportional to the square root of T. Velocity is directly proportional to the square root of T. So V1 over root T1 must be equal to V2 over root T2. So based on this, we have V1. Okay, there was no V1, Abi. It was R that we were relating with, Abi. What R are they relating with? Read the question out.
What temperature will the molecule of an ideal gas have twice the RMS speed?
Twice the RMS speed, yes. So it was not velocity and temperature now. I was supposed to be looking at maybe the AVG. So how does it relate? How does kinetic reason relate to what we're doing? That's the issue. There's no mathematical relationship. Let me see.
I tried to.
Okay, based on two pages.
I just tried to.
Okay. So when you twice the temperature, that became 40. Sure, that's how it works. It's wrong. It's wrong. The method you're supposed to follow is this, but with R instead. With R. And it is our time followers. Even if you wanted, well, so what are we doing? See, the relationship is between what and what? R and T. Root mean square and T. So this is the root mean square here. Where is it? The root mean square velocity. This is the T, Abi. So we are picking out the root mean square velocity. That was what I did here. So let me just let me use the word VR1 so you will know. VR2. You get? So this is root mean square. I wrote it as R here. Let's call it V. Since we've used V here. Do you understand? So from there now we have what? From there now we have what? This T1 is 20, right? So I'm having VR1 over square root 20 equals to okay, Kelvin, good. So 293 equals to what? Nice. Not wait. I don't know what I wrote. What was it before? I think we're looking for what it will make it become 2 times of what it was having. So here's my V2. 2 times of what it was. 2 times of what the other one was, Abi, divided by T2, which is what we're looking for, Abi. So this one has cancelled. This one remain 1 here. So 1 over square root 293 is equals to what? 2 over T2. Let's multiply. T2 equals to what? Where's your calculator? This thing we calculated now. We're calculating temperature, right? So this is 34 Kelvin. So it is at 34 Kelvin that doubling exists. It's correct. This one is correct. So let's have another one. Setting the root mean square speed. The RMS speed of nitrogen molecule is about 490 meters per second. Is about 490 meters per second. Find their mean free paths and the average time. Find their mean free paths and the average time. The mean free path and the average time between collisions. Stop. The radius of a nitrogen molecule can be taken to be the radius the what I said, the radius of a nitrogen molecule can be taken to be the radius of a nitrogen molecule can be taken to be 2 times 10 raised power minus 10. 2 times 10 raised power minus 10. 2 times 10 raised power minus 10. How is it going? So we have n over v equals to 1 for the root mean part formula. N over v, or just instead, make it straight up. The mean free part is P equals to K subscript B. That is Boltzmann constant multiplied by temperature divided by 2 pi and 4 pi. I said P is equal to, that's the part. The part is equal to what? KBT all over 4 pi roots. 4 pi roots. 4 pi roots 2b square. KBT. So that's that. Are you done with it? But you know how to use the formula now. Just to substitute those things there now. Eh? KBT. Temperature is there now. What did they give you? No temperature. Okay. No temperature. Okay. Can you read that question for me again? Uh-huh.
Find the mean part, the mean color, and average time between conditions. The radius of nitrogen molecule is 2 times 10. This one minus 10.
No. Let me see. Use this other formula. I think they gave you, did they give you something like volume? Stuff like that.
490 meter per second. No.
Only, for like, only,
And radius. Only radius and mass.
radius and mass. How about the specific, I mean, specific. How about the rhythmic square? Read the question out.
RMS speed of nitrogen molecule is 490 meter per second. Find the mean time pass and the average time between conditions. The radius of nitrogen molecule is 2 times 10 to the power minus 4.
So, root mean parts. Since they didn't give that parameter, they were supposed to give you the normal. The value n they were supposed to give to you. Just don't get it. Can't find it here. I will try to check tables. They're not there. What is it? All right. Copper bar is 80 centimeter long. Copper bar is 80 centimeter long at 15 degrees Celsius. Copper bar is 80 centimeter long. 80 centimeter long, yes. At 15 degrees Celsius. 15. What is the increase in length? What is the increase in length? What is the increase in length when it is heated to 35 degrees Celsius? When it is increased to 35 degrees Celsius. When it is heated to 35 degrees Celsius. The linear expansion coefficient for copper is 1.7 times 10 to the power minus 5. The linear expansion coefficient for copper is 1.7 times 10 to the power minus 5. Per degree Celsius. That's the unit. The unit. Do it. This is from linear expansivity. So what do you get? So yeah. I didn't hear you. Okay, look at what you're using. You're going to be using. You're going to be using this stuff. That's linear expansivity. This L1, theta 2, and theta 1. What are the things they give to you? They've given you two thetas, Abi. They said we should calculate the increase in length, Abi. That's what they said. They don't say we should have to calculate new length. The increase in length is the same thing as instead of writing L2 minus L1, I'll just say change in L, Abi. So we're looking for this change in L, and it's equals to alpha L1. What's that thing again? That's there. So they need to change it. For this one, they need to change it. How's that mean? 10, 20. It's 20. What's this guy? 7 times 10 is power minus 5. Times what's this one here? 80. 20. 160. 160 times this one is what? 7 times. You're just anyhow. Zero point. Everything together. No, you're not. Let's go for another one. All right. Well, I can't see more questions on that aspect. Hmm? All right. Find the RMS speed of a nitrogen molecule. Find the RMS speed of a nitrogen molecule. Find the RMS speed of a nitrogen molecule. In bracket, M is equals to 28 kilogram, 28 kilogram per kilomole dot mil dot millimeter dot mil mml, that's it, in air as at 0 degrees Celsius. As at 0 degree Celsius. As at 0 degrees Celsius. Don't make mistake, we'll solve small, carefully. That's elapsed. Okay. I want to use myself. This is our page. Mando. No, I want to just use myself. Okay. So, all right. So let's run through on that. So yeah, we we treated the molecular assumptions. So we're going to be looking at the empirical laws. We're going to look at the empirical laws. So when we say the empirical laws, we're talking about the gas laws. And these gas laws, they describe the behaviors of gases. They describe the behavior of gases. And we'll be describing them alongside with exploring necessary graphs that needs to be explored. Yes. We're going to be discussing Charles' law, the Boy's law, the pressure law, We'll talk about Dalton's law. Okay, this is physics. Talk about avocados. And we'll talk about the Nigerian gas. Okay. So, starting from the first one, which is the Charles law. So what do you mean by Charles law? So for a fixed mass of gas at constant pressure, that's one of the most important things here. At constant pressure, which shows us that this is true for an isobaric thermodynamic system. Constant pressure, the volume of a gas is directly proportional to its absolute temperature. And when we say absolute temperature, we're talking about temperature in what? Temperature in what? Temperature in Kelvin. Good. So this is the mathematical relationship and the constant generation. The graph is true like this for the velocity against, the volume against temperature in Kelvin. And about if it was volume against, how about if it was volume against temperature in degrees Celsius? You know that this point here, when it's 0, is not equal to this point here when it's 0. This point is called absolute 0. For now, scientists have not been able to hit or get any object to that level. So you have something like this. -273. So that's it. That's it. Right, next. So first thing I want to highlight here is that Boyle's law, the graph is an hyperbolic graph. It's an hyperbolic graph. It says for a fixed mass of gas at constant temperature, the pressure of the gas is inversely proportional to its volume. We had mathematical expressions. Those mathematical expressions were true. Next one. We had pressure law. Statement: for a fixed mass of gas at constant volume, the pressure of a gas is directly proportional to its temperature. So this one is given that volume is really constant. That's isobaric and isochondric system. So that's the graph there as well. Yes. So we have the combined gas laws. We have the combined gas laws. The combined gas laws, it shows the relation between usual volume and absolute temperature, and it's given by this expression. It's given by this expression. So these are the components. It's from the combined gas law you get the ideal gas law, but they are not exactly the same thing. Regardless, for a fixed mass of gas at constant pressure and temperature, the volume of the gas is directly proportional to the number of moles of the gas. So that's it. That's like saying equal volume of all gases at the same temperature and pressure contain equal number of molecules. Ideal gas equation. An ideal gas, the pressure, volume, absolute temperature, and number of moles are related by this. That's what you're asking about, right? That is the PV equals to nRT. PV equals to nRT. Where pressure, Pascal, volume, is meter cube, number of moles, mass, mole, absolute temperature, and change in universal gas constants. So when we hear the universal gas constant, universal gas constant is the proportionality constant in the gas. Yeah. So next. So another law of partial volume, right? So in this one, what we are doing, it's not a common law. We're not dealing with the summation of partial volume. When you are having numerous number of volume or mixture of volumes that do not mix, right? You can make use of this and like that mixture of volumes. So it says the rate of diffusion of the gas, that's not it. Okay, I've changed it. Yeah. Volume of a mixture of non-reactive gases at same temperature pressure is mainly sum of the partial volume. So it's just like your law of partial pressure. So for partial volume, right? This is Graham's law of diffusion. Those are they're not physics courses. Nevertheless, Graham's law describes how the rate of diffusion of a gas is dependent on their molar masses as a whole. So if you have a large molar masses, you won't diffuse very well. You won't infuse very well. Just the fact. Alright, I'm not answering the question there. That's nice. Molecular diameter D. Definition. The molecular diameter D is the effective diameter of a molecule, assuming molecules are hard spheres. Method of determination from viscosity measurements, from diffusion experiments, from kinematic. So, degree of freedom. The degree of freedom is the number of independent ways a molecule can store energy. It's different ways molecules can store energy, right? So what are those ways that molecules store energy? Type of molecules and degree of freedom. We have the monoatomic gases. Those ones have rotation, non-linear. So, molecular speed distribution. Gases consist of a very large number of molecules, which gives the wide range of speed. Molecular speed distribution describes the relative speed of molecules having different speed at a given temperature. So we should understand that these concepts are part of it. Sound have molecular speed, we have instantaneous speed, as well as average speed. The most probable speed is the speed at which maximum number of molecules are moving. Expression C and P was 2kt over n was 2RT over n2. This ones are if they ask you for most probable speed. If they ask you for VRMS, you are using what we did earlier, which is the 3kt and 3RT. Okay. This one is for average speed. Okay, go back first. Number 10. Okay, now you remember the root means from that. Alright, go for it. This stuff is something that you have gotten exposed to the foundation by now for our students. I've been dealing with more complex appearances. I've been dealing with more complex appearances. Next. That's how my distribution is. So we have boys law and child's law. Do you understand boys and child's law? Good. Good. So I'm supposed to be effect of temperature on distribution. So when there's an increase in temperature, shift the equilibrium curve right and make it broader and flatter. So relationship between Boltzmann constants and gas constants. So from there, I see that regardless not number is always on board. So the internal energy, internal energy of an ideal gas. So the internal energy is the total microscopic energy possessed by the molecule of a gas. So that's the key thing, because I don't think that definition is going to reappear anytime soon. So when you get internal energy of a system, it is the sum of all the microscopic, both kinetic and potential items of that time. We visualize on ground. Therefore, when I do gas, microscopic interpretation of internal energy, molecules of a gas are continuous random motion. And then energy arises in the So, in microscopic view, molecules move randomly in one direction Each molecule has translational kinetic energy. They move straight, right? Propagated straight. Due to motion along X, Y, and Z. Some molecules are diatomic and polyatomic. Some have rotational and vibrational kinetic energy. In an ideal gas, potential energy is equal to zero. There is no intermolecular force. I'm going to solve questions on it very soon. This is this place. So my microscopy is about of the energy. So characteristics of internal energy of a diatomic gas. Molecules have bonds between two atoms, right? For diatomic gases, the gas is the atomic element is made up of two atoms, so there will be bonds existing between those two atoms. And one way or the other, the kind of energy that exists within them will determine the level of their degree of freedom to determine it. So here we wrote the internal energy with this kind of expression, then about that internal energy, this kind of expression, we have that. We're going to look into them. So start from here, rotation about the bond. Rotation about the bond has requires very little energy and is usually not excited. But when we come to types, every single one of them experience excitation due to the kind of activities going in, except for vibrational. The vibrational is a sequential periodic to and follow. First, we start the individual of the object, things become too monotonous if it's somebody who is a human. And nobody able to be effective with such a job. So, for polyatomic gases, for polyatomic gases, I just want to change the mic. One is what's in my ear. So yeah. Okay. So energy contributions per mole. Translational 3, rotational 3, rotational 3, right? Energy contribution per mole. So we have this. So this one's own energy, vibrational own energy contribution per mole is 2. That's why there's nothing at the back of the RT. 2 over 2, 2 cancel 2. But vibrational has both 2 for non-linear and 2 again for linear. So, next slide. dependence on temperature. An ideal gas, internal energy depends on temperature. Yes, internal energy depends on temperature, pressure, volume, or amounts do not affect U for a given T. General relationship. General relationship is this. You don't do that. U must be equal to F over 2 nRT. You can't change this setup. So, specific heat capacities. We've done that. We've run through specific heat capacities. You see? Next slide. We've run through specific heat capacity. Next. Let me go back first. Let me see. So, various relations and ratio of specific heat. She made it clear that CV minus CU equals to R. It's a masterpiece. She has not just reflected it in the whole of the university's environments. All right. So, okay. As values for ideal gas. Linear relation and ratio of specific heat. So we usually utilize those expressions there when we are dealing with thermodynamic system for heat. The R, Cp minus Cv, that is specific heat of gas at constant pressure. You can write it down. And the Cv is specific heat of gas at constant volume. You can also note it. Lesson here. So on the other hand, we have Cp over Cv, and we also have Cp over Cv. Typical values of Y for ideal gas. So those things are most likely range that works, that are constant. Monatomic gas, the degree of freedom is 3. And that's why you can stay anywhere, you can go anywhere. Go anywhere. The atomic gases, on the other hand, have an even much higher degree of freedom. Those that have 3 degrees of freedom are even still a bit confined. 3 can live at any point in time. So the polyatomic type of gases, those ones, they move, they can move extremely freely, and for that reason, they are the one that attributed the lowest column. A column there is an antisocial column, in the sense that the more you go down the column, you find out that those particles there have much higher degree of freedom. So, next slide. Thermodynamic process involving ideal gas. Actually, before we start talking about the thermodynamic gas involving ideal gas, there's some things you need to understand. Can you hear me? Actually, you can hear me. Or should just. Okay. So, thermodynamic processes. You can see we have a large number of processes, but yet only a few number of people are working in those kind of facilities. So they would rather not employ anybody than employ who is up to the job. So we have certain thermodynamic processes. We have the adiabatic process. We have the isochondric process. Can you hear me? This is important, very important. Isochondric process. We have this isochondric process is also referred to as what? Isovolumic. We have the isothermal process. And then we have the what now? We have the isobaric process. So we're going to have to be showing the implication of these three processes on the thermodynamic laws and equations that we have, starting from the first law of thermodynamics. Starting from the first law of thermodynamics. Do you get what I'm saying? Okay. So, brief explanation of each of them. And the adiabatic process is one in which there is no heat transfer. Heat is not transferred into the system, and it is not transferred out of the system. That's what we call adiabatic. But when we say isothermal, this one is one that is occurring at constant temperature. Isothermal is a thermodynamic process occurring at a constant temperature. But this one here is occurring at a constant what? Volume. Isobaric process, constant, occurring at constant pressure. It comes from the word bar. When you hear the word bar, we're talking about pressure. So That's that for that. So normally we have this our thermodynamic equation, and our thermodynamic equation themselves themselves we say the amount of heat transferred equal to work done. I can just write equals to Q minus the work done. And that work done are of different types. This equation can be written in many ways. Some people can write it with the plus, some people can write it with the minus. Depends on the sign convention that they intend to do. You get? So basically, U is equal to this and this. It means that the value of the internal energy is usually dependent on if heat was transferred in or out, and if that's capitalism, maybe from anywhere, maybe doing work on the surrounding, or the surrounding doing work on you, anything at all that is bringing heat into the system, that's part of it. It's just like your normal economy, where aside from normal transfer of heat like Q, other things can bring in funds based on work, right? That's how it looks like. So eventually, the total summative effect of all these things will contribute greatly to what the internal energy of this U should be. Do you understand? So it's as simple as that. It's as simple as that. So let's start from there. Adiabati. We can start from the thermodynamic equation. Let's start from the thermodynamic equation. Let me use plus on my own. I'm going to be using the convention that brings in minus based on what W is doing. Do you understand? Based on what the W is doing. So sometimes W can be work done by the system of the surrounding. Sometimes it is work done on the surrounding by the system. You understand? So these technologies are in a large way possible to generate. I get you now. But you need to understand one thing. Well, what is it? So if I have W, can be work done on system by surrounding. We also have work done by surrounding system. Right? Yes? Can you? Okay, bedroom break. Okay, that's fine. You are still here. When I said, while I wait for hour, I'll give you a question. So then. So I wrote work done off the system, sorry. Work done on. It's by. So if I'm doing work on the system, is going to be increasing the amount of internal energy in the system. Eventually, only few people are like that. So work done by the surrounding, that means the work done by the surrounding is being done on the system. And that kind of thing will increase the internal energy. It's going to increase the internal energy. It's going to increase the internal energy greatly. Same thing with this one, work done on the system by surrounding. Since it is surrounding that is doing work here, the surrounding is one doing work on the system. It's going to benefit the system more. It's going to benefit the system more because the internal energy of the system will go up. Yes. The energy of the system will go up. So let me find some questions that we can solve from this first aspect that we've done. So that we can solve those questions. So the ideal gas equation that we spoke about here and the general gas equation, they are both very similar. The only difference is that one of them brings in a constant that we serve as a relationship. So cause recursive comparison. You're having your P1, V1 over T1, P2, V2 over T2, like that, instead of just the PV equals to MRT, right? So all those things are like intentional moves to make sure that it sticks to your brain. So all right, let's solve the questions, please. All right. Thank you so much, everyone. An ideal gas, an ideal gas is in a chamber at a pressure of 2 Pascal. Is in a chamber at a pressure of 2 Pascal and has a volume of 20 liters. And have a volume of 20 liters. Have a volume of 20 liters. When at a temperature of 298.15 Kelvin, determine the number of moles of gas in the chamber. Determine the number of moles of gas in the chamber. Determine the number of moles of gas in the chamber. So that's that question. Let's solve it together. Read it out. I'm not leaving it for you. Like, it's in the chamber, right? And it's measuring what? That means that's the pressure. P1 is equals to 2 Pascal. You get that now? You get that? Uh-huh. And a volume of 20 meters. So we're having V1, that is, yes, volume of 20 meters. V1 is 20 meters. Meters cube, I mean liters. Liters. Uh-huh. Next. Temperature 1, 298.9 Kelvin. Uh-huh. Number of moles, Abi. So good. With the way all these things are, the fact that my volume is liters, I will use the gravitational constant that has liters, which is 0.0821. And the unit is what? The unit is what? We have what for the unit? Look at this formula here. PV equals to nRT. If you do this, you'll be having PV over over NT is equals to R. So therefore, you can see what your unit is. PV, that is ATM. Yeah, I'm working with Pascal, right? Pascal liters, right? Right? So although we can still write it as ATM because they have their relationship. They do have their relationship. One ATM is equivalent to 100 and something Pascal. So it depends on what you want to do. You can decide you want to convert it. It's fine. You don't want to convert it. It's still fine. All right. So yeah, we're having, what are we having? If I thought I would start getting used to it, I would advise you to just convert it. How do we convert it? 101,000 Pascal is equal to 1 ATM. Because actually ATM you're supposed to be using here. So therefore, how many ATM are we, okay, we have 2 Pascals here, have we? So therefore, 2 Pascals should be equal to what? X. So because multiply. S is equals to what does it give you? 0.000 what? Times 10 is power of what? Okay, that's here. 1.98. 1.98, right? Times 10 is power of what? -5 ATM. So let's put that ATM dot liters dot what now? Dot what now? This is the expression here. Dot Kelvin dot mole. Are we there now? So R is equals to what? What is it? Okay. Sorry. So we are having this formula here. PV is equals to nRT. So to find N, we're having PV over RT equals to N. So yes, PV over RT equals to N. Okay, thank you. So PV over RT, we're going to just substitute everything now inside. We're going to be substituting it inside. So I'm going to be substituting all the values that we have inside so that we can get what we are looking for. So we're having 1.98 times 10 raised to the power minus 5 multiplied by volume, 20 liters, divided by R, 0.0821, multiplied by T. Where is T in this place? Didn't call T for me? 298.9. One point six one times 10 minus what? Normally. Okay. 1 point what? Okay, that's fine. I've heard what I'll do. Okay. Okay. Write this other one down now. A 50-liter cylinder is open to the atmosphere. A 50-liter cylinder is open to the atmosphere. A 50-liter cylinder is open to the atmosphere. It is then sealed. It is then sealed. It is then sealed. It is then sealed with a piston and compressed down to 10 liters. The temperature is kept constant. Yes. A 50. Where did we stop? It is then sealed in a piston and compressed down to 10 liters. If the temperature is kept constant, what will be the new absolute pressure? What will be the new absolute pressure? So, give me, quick. $50 what? So that's what? Uh, temperature is constant. What was the pressure when it was V1? Read the question out. Maybe the set standard temperature or pressure. So you see that bit that they said exposed to the atmosphere. Try to tell you that atmospheric pressure was acting on it, which is 760 milliliter mercury or 180 m. So P2 question mark. So that's how we do it. So we're having V1 P1 equals to V2 P2. What's our V1? 50 times 2 V2 is what? 10 times question mark 100 is equals to 10. We are looking for P2. So let me start by 10. 10 what? ATMs. That's quite a lot of it. Yeah. Okay. All right. So let's see if we can touch on one thing. Wait. It's complete 1 hour. Okay. So let's pick one more question. Thank you. Thank you so much. Let's pick one more question. The gas is sealed up into a closed container. The gas is sealed up into a closed container. The gas is heated so that its temperature rises from 100 degrees Celsius to 200 degrees Celsius. From 100 degrees Celsius to 200 degrees Celsius. Full stop. If the initial absolute pressure in the container was 2 atm, what will be its new value? Did you write it down? What will be its new value? Gas is sealed into a closed container. Okay, you got it, Abby? You able to write it? All right. So let's solve this thing quickly together. Help me with the parameters, shall okay, T1 is what? T1, 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 T1. Hello. T1, T1, T1. So we assume so we assume no. So we assume that T1 give me the values, give me the values. T1 is 100 degree Celsius. T2 200 degree Celsius. Yes. Nice. P1 is 2 atm. So we are looking for P2. So what do we use here? P1 over T1 equals to P2 over T2. So P1 over T1 equals to P2 over T2. You can hold it. So I'm having P1 is 2 over 100 equals to P2 over T2, which is 200. And cross multiply by having 100 P2 is equals to 400. Then we have this. P2 is therefore equals to what? 480. So that will be that for that. Thank you so much. Thank you. Right, right, low, low, right. Yeah. So we are going to be commenting and we are looking into thermodynamic processes. So we're looking into thermodynamic processes. So when you hear the word thermodynamics, what comes to my mind is change of state. We're looking at change of state. We're looking at change of state of a system from one equilibrium state to another. So the path followed by the system moving from the initial state to the final state is called the process. Understand? So the path which we follow to move from initial state to final state is what we call the process. So key points. Processes describe how PVT and other properties change with time. They are represented on the P, V, T, V, and PVT graph. And as well, we are plotting graph of P against V, or T against V, or P against T. Those diagrams is easy to us. On the other hand, we have work and energy. Each of them depend on pathway, depend on the pathway of the reaction. So for our ideal gas, PV is usually equals to gravity. And it always holds true for equilibrium states. Processes covered. We have quasi-static process. We have reversible and irreversible processes. We have isothermal process, isochondric process, isobaric, adiabatic, polytropic processes, cyclic process for expansion, and entropy process. Next slide. Next slide. So we've talked about each of this process one after the other. So a quantitative process, listen up. A quantitative process is a process that passes through a continuous series of equilibrium states. The process that passes through a continuous series of equilibrium states. Well, then we have a number of states of equilibrium, and it gets to those places, leaves those places, returns to those places. So it achieves equilibrium repeated number of times. So the change is made infinitely slow. Quantitative states, they are made infinitely slow. They are not quick. Understand? Pressure and temperature of the system are always infinitely different from those of the surrounding. Yes. Such processes can be represented and well defined using the PV, TV, or PT code. So, when you look at that diagram there, there's an example of a quantitative. And each dot represents a series of equilibrium that were attainable. So we have reversible process. The reversible process is a process if the system can be returned to its initial state and infinitesimal change, there will change in their surrounding. That's like completely undoing what has been done. Because if you should reverse time, or you reverse events, there will be a huge disbalance, huge imbalance in the world. Do you understand? So though precipitating effect like friction, viscosity, turbulence, and etc. exist in reversible processes. So comparison, reversible processes, they are ideal. They have no entropy generation. But they don't have any entropy generation, and the entropy is usually equal to 0. They are also irreversible, but they have real, and the entropy generation is low. So irreversible process. The process is irreversible if the system cannot be returned to its initial state without leaving anything untouched. The environment will continue to be a reflection of the present. To involve finite ingredients and dissipative effects. Less work is obtained for those that do, just like all natural processes are irreversible. Example of irreversible: friction, heat transfer, and cross-planet temperature difference, fluid expulsion, and then we have mixing. So that's it. So an isothermal process, the process in which temperature remains what? Constant. For an ideal gas, PV is equals to a constant. PV is equals to constant. Work done by the gas is then given by work equals to MRT ln V2 over V1. This is exchanged. Then change the energy will be equal to 0. That's an isothermal process. Do you understand? So what I want you to pick note of there is that the implication of an isothermal dynamic, an isothermal thermodynamic process is the fact that change in U is equal to 0. Isochloric process, also referred as isovolumic. Also referred to as isovolumic. So in this one, volume will remain constant. One ideal gas, T is equal to constant. Up, down, constant. Heat exchanged, constant to change in the energy. And that's it. So down there is the graph, T2 and TV. Let's put it on this plate. So we have isobaric. Yes. Yeah. So take front ones. Take it front ones. Yes. So isobaric processes are processes occurring where pressure is constant. Where the pressure is constant. And for an ideal gas, it's important for you to know that V, that T, in the holding is actually one of the biggest constant Ks that you ever have. Yeah. So mole is equal to P over V2 minus V1. Yes. Change in energy equals to LCV. So that's it. For adiabatic process, Q is equal to 0. No heat is exchanged. It's surrounded. For a reversible adiabatic process, GV is equals to constant. Work done, which is W, is equal to that. So we have to keep the expressions in our head, just in case you might want to use it to solve. We're going to have the answer. So we have an adiabatic curve. This is steeper, and an isothermal curve. Let's say it's constant. PV diagram. This is when the line is straight. It means the pressure is constant. It means the pressure is constant. Next. Next thing. So, free expansion and tightening process. Free expansion gas is expanding to a vacuum when there is no external pressure. And then the gases all done is now equals to zero. Heat transfer is now equals to zero. When it's probably insulated, change in internal energy is equals to zero. And an ideal gas change in temperature is equals to zero. Thermal process, Joe Thompson, one that discovered it. Yeah, so we have gas moves through bronze proton coil. That makes it work. That doing the external work. Heat transfer Q and the electric process. Enter here Q, the electric, which means that the heat transfer is not occurring. There is no heat transfer from one medium to another medium. No heat transfer. So in the throttling process, there is a change in enthalpy. You see that there's a change in enthalpy. That change in enthalpy has a value is equals to what? 0 greater. The enthalpy change in throttling is equals to 0. But temperature it decreases and increases depending on the gas and the initial condition. If the gases, the hot gases, they will blow hot, and the cold gases, the cold gases, blow cool, blow cool. Application for cooling gas powered refrigeration system. Next slide. Next. Water. Gas. When a gas changes from one state to another, it exerts pressure on the surrounding and work is done. So whenever there's a change of state, just know that work has been done. I can tell you that work has been done. Sometimes it's through pressure, and you just do it just so that you can fit into the competition. Do you understand? Okay. So, key points. Work is done by gas when it expands. But when it contracts, when gases are expanding, they don't want to do that work by themselves. When they are contracting, it means something else is doing the work for them. Something else is doing the work for them. Work is done with gas when it's compressed. So the work done on the path fluid between the initial final stress so on the PV diagram, work is done the line process code. And then contemporary before. So, general expression, W is equals to V1, V2, as the definite integral of P, where PV is this, so when the velocity, the volume, is this, complete. Okay, next. So, over, yes, the pressure remains constant while the gas expands. That's an isobaric expansion. We need to understand what happens in each expansion. During the isobaric expansion, the pressure remains constant while the gas is doing it, expanding. How is the pressure remaining constant? Why is the gas expanding? So, derivation says, of the P, second derivation is 1, after the V, and then we bring that from 2 to 1. Others will do it, nothing happened. Nothing happened. So that's the one. So the good thing is that for isobaric system, you not just think that, oh, the pressure is no longer acting. We have multiple pressure pipe. You use multiple pressure pipes, you have plenty of them, so that you're not using your phone. All what you do is charge the phone, and then you have instead of back, and then you have this. Okay. That's speaking in means. That was not physics. So, I know I explained this already earlier. Next slide. Now, what's isochoric process? It's also referred to as isovolumetric, or what we call isovolumic. The volume remains constant, the gas does not expand or compress. That's isovolumic. In that case, looking at this, right, and the percent is equal to 0. Because work is not done on the gas. The gas is not expanding. The gas is not what? It's not contracting. Just what I'm saying. Isochondric, constant volume. So there's no expansion of gas. So there's no work done by you or your other guys. Right? If you are considering stop doing this, you need to rest. So that's that one for that. The first one. PV diagrams. Since there is no change in volume, the boundaries do not move. Therefore, no work is done. If no work is done. Application. Heating or cooling in rigid containers. So, next one. Work in isothermal expansion and compression. So the thing is, when temperature decides that you want to remain constant, it can result to both whether expansion can also result into compression. So W is equals to work done is equal to this. Evaluate the V volume. Pick out the volume. Take it separate. This expression here is the same with this. Because this is you bringing it out, you integrating 1 over V, gives you really V. Then when you put it in, you understand better. That's at this point. This side here. After this one. No. You are tired of the integration. It's just integration now. To integrate this kind of thing, this is what you do. Great space. But they can ask you to do it. So they have the equals to T. They now have people that look like they respect your space. Like W equals to this. What do you have here? The S. NRT over V. Right? So dV. What does that now give us? All these ones that are now V, carry them out. Because you cannot integrate them. You can only integrate the V component, that stuff that has V. So that means this expression is the same thing as W is equals to NRT, everything else out. It's really 1 over V, dV. Yes. All this goes together. So by the time I want to now deal with this, I don't want to integrate this. If I want to integrate 1 over X, it gives you ln X. So if I want to integrate it now, I'm ready to be using ln V for any question on this. W now equals to NRT ln Euclidean V volume for you over V. What is it? Last 3 seconds. What I said, I don't remember. V2 over V1. Yes, now normally what's supposed to be here is in V like this, have it? But you know this thing here, that's open to the other. Vx towards Vi. So you say W is equals to NRT ln open bracket V2 minus V1. That's what it is. That's what it is. That's what it is. So, consider that's everything happening there, right? I believe you all know that when you see minus in front of a log, same thing as division. Log A minus B is log A over B. So this is going to be like first narrative. So that's it. That's it for that. Next. Next. Go back. This is adiabatic. So in adiabatic, there is no heat change. The surrounding, no heat change. For a reversible adiabatic process, for an ideal gas, PV is equals to constant. PV is equals to a constant. So W is equals to the same we did it the same way. What is the word around? I think we want to make it different. Yeah. What is it? What? What is it?
W is equals to 1 over A. Y over. So should be that that's integrated by that just integrated by outside.
This one?
Yes.
Yes. So, what do we now have? We have work equal to V2 V1. This is what it becomes when you have integrated it. This is what it becomes when you've integrated it. Where your y is your what? Is your CP all over CV. This CP is called specific heat at constant pressure. YCV is called specific heat at constant volume. And our CP is usually greater than our CV. Okay? Right. So the next slide. Remember I'm giving you this equation, right? I said there's some science convention I'm going to use on it. So it depends on how you want to use the same convention. Now tell me what's going to stay in the equation. Equation of what? Any equation that I want to use, I'm really trying to make sure that we master the equation properly. That we don't just use them anyhow and underuse them. We understand the utilization of the movements you just made. So, he changed the sphere of the Najawa mathematical formulation. So, Heat added to the system. When heat is added to the system, now Q is positive. This in the root as greater than 0. Let me just write it here. Talk about that. Q is positive. When it is less than 0, it implies that heat is taken away from this slice. Heat rejected by the system. Sometimes the heat did not go, but they don't reject it. Because now they just went to his own house. So, so W greater than 0. W is greater than 0. So the work done by the system. See that? So that one is 0. So when work is being done by the system, we're having 0. Work done on the system will give you what? 0. So okay. So it added to the system, heat rejected from the system. Heat added to the system is what it. Okay. Next. Application of various processes of energy consumption and energy balance. Was an thermal process. So energy conservation and energy balance. Process Z. Conditions Z. Work for W Z. This law also Z. So we have that process. So in an isothermal process, T is constant, meaning that U is equal to 0. Because internal energy moves hand in hand. It's okay. Okay. So let's take it from here. Isothermal. This is a summary of the processes that we have been talking about since yesterday. And this shows this condition, which shows this work formula, and shows in our first law that Q is equals to W. It shows that, and it satisfies it. Isochondric shows that V is constant. Comes here and help us see that W has to be equal to 0 for isochondric. And then there is no work expression for it because W is equal to 0. But in our equation, you can see it there. Then isobaric is where P is constant. P is constant, but here we record a change in volume. That means there's a specific value of P that is acting to create that change in volume. And that's it here. All right. Last one, adiabatic. Adiabatic is that one that we should say heat transfer does not exist. There's no heat transfer. So this is the formula we use after integration to get that adiabatic stuff. And based on first law, it means that the change in U is equals to W. Then polytropic is just your arrangement, your personal arrangement. Like you are arranging this, and this, and arrange another way around. I can always arrange my own another way around. I can always arrange it another way around. Yes. Yes. All right. All right. Next slide. Second law of thermodynamics. Second law of thermodynamics. The law determines the direction of natural processes and sets limits on the conversion of heat into work. It helps to set limits on the conversion of heat into work. This law determines the direction of natural processes. Then what are the importance? Heat cannot be completely converted into work cycle. You can completely incorporate it into a work in cycle. Entropy of an isolated system never decreases. Never decreases. Defines the efficiency limit of heat energy and generators. Heat engine and refrigerators. A heat engine is one from a hot reservoir. It's one from a hot reservoir. Convert it from a hot reservoir into work by rotating some heat in a cool reservoir. So that's the hot reservoir where we store the hot reservoir where we store machine equipment, hot fluids, precisely, to cool them down. So when they get into the engine, it can later be released into the cold reservoir. Is the engine that I lost heat. So that's why you see us do the whole. When you are doing work in here, we are doing work out here. And here just a QC. Has no purpose. So that's it for it. So and the pump is similar to a refrigerator. That is how they run the pumping. This reservoir is similar to a refrigerator, but used for heating purpose, for heating purpose. Yeah. Next, thermal efficiency and coefficient of performance. I did tell people this. So, thermal efficiency and coefficient of performance. So, in the efficiency, I'm assuming that is not clear. How to be this? So, oh, Jean, QH, that's the hot reservoir. Why did you see represent a cold reservoir? So in the engine, which we are about to enter, we have hot reservoirs and cold reservoirs. We have hot reservoirs and cold reservoirs. Okay. Key points. Higher efficiency, COP. That's for heat engines. Carnot engine gives the maximum possible efficiency, where the Nmax, that is the efficiency, equal to 1 minus Tc over Th. Yeah. So, no, but you can gain, they might not both be able to absorb, but the process can occur. We're not going to be spontaneous. That's been engineered to do so. So, cannot refrigerate up. I've never used such generator before. It's very different, very useful. Visible. It's no matter. So, next. So, higher efficiency or COP means better performance. COP stands for coefficient of performance. So when you have higher efficiency or higher COP, it means better performance. Carnot engines give maximum of it, which we said earlier, cannot refrigerator give the maximum coefficient of performance. So yes, under the that's why I see refrigerators and pump. Next one. Next slide. What is there? Stay. Okay. Can please help me call somebody on this slide? So, entropy and ideal gases. The concept of entropy. The concept of entropy. Entropy and ideal gases. So, entropy is the thermodynamic process and property that measures the degree of what? Of a system, right? To measure the randomness and disorderliness of a system. Key ideas: we have a natural variable for a reversible process, represents the unavailability of energy to do useful work. For an isolated system, we have this, right? An isolated system, entropy greater than 0, and it is 0 for perfect crystals, absolute 0 temperature. Surroundings to system, showing direction of motion. All right. How about definition of reversible processes? The entropy change for a reversible heat transfer at temperature T is defined as this. You understand? Which thing? Is our security. There's nothing again. D is equal to S Q over that. But what we know is that this Q normally is quantity of heat flow. SDN has its own value. Could be anything. You can't tell. So, but here now, because we're dealing with entropy, we're dealing with thermodynamics, we know that that is going to be entropy. And this SCL is entropy. That thing there is like a fractional change. Small change. I know, I don't. No, I know composition. God himself there. A finite change in S is equals to that. Then properties, the state function, the state function. Each differential, exact differentials. Change in S depends on initial and final state. Additive or composite systems. The state function is any function that depends on the property of the initial and the final state. I get it now. Like entropy is a state function. No, it does not necessarily have to depend on the part. All we just want is you must depend on, or you must have initial and final. You must be able to use your and do all these final and initial kind of things. Temperature, we don't know. The temperature is the general reason for studying gases. Entropy, gypsum. Every single time you're writing them, you're writing them as this over this. Are you getting this now? Exact differential. So that's what you're doing in class already. Okay, you're not medicals. People have done it. That's like definite integral. Entropy change in the isothermal process. So for an ideal gas undergoing reversible isothermal process, change change in S is reducing. Sorry. For an ideal gas undergoing a reversible isothermal process, the change in S is equal to this expression T. I don't know, which is equals to, we care more about what is inside it because that's what we want to integrate. It has the quantity we want to integrate. These are complex quantities. We would talk about them as we go on. Yes, talk about them as we go on. Therefore, change in S, which is my entropy, is equal to NR ln V2 over V1. I think I've explained that part to you. I explained that formula, derived that formula to you. We did the derivation. That's what we did the derivation together. Okay, you can see the graph of the PV. See the graph of the PV. Expansions of goals we change in S is 0. Equation of goals we change in S is less than 0. Okay. Alright. So entropy is increases during expansion and decreases during compression in an isothermal process. It's very, very important to know that. Very important. We'll go to the next slide. Okay. For a reversible isothermic process, like materials, you have that expression. Your Q is equal to NCP dt. Very important. For the surface, C is your specific heat at constant pressure. CP, specific heat at constant pressure. Do you ever get that? So, and that's that. So we have entropy increases with heating and decreases with cooling. Rapid graph. So, there we have it. There we have it. Next time. Working as a caloric process. And see, now it's a caloric process. Volume change is what? Volume is constant, so there's no change in volume. So that means it doesn't take work in that aspect. This diagram shows you that pressure might be changing, but it's not causing change in this other side. Time pass. Time time. So, like I'm telling you. Okay. Sorry. Just a minute. I'm back now. Yes. So, yeah. So, the volume remains constant. Okay. I think I've explained this as one drink. So next, adiabatic. So in an adiabatic process, you know that Q is equal to 0 as the quantity of heat transferred is equal to 0. So therefore, you know that this entropy expression, you know where you get this entropy expression from? So this entropy expression, entropy is equal to this. You can integrate it. When we integrate it, then you will get those expressions. So look at the sign. When entropy is S, it goes to 0, that means it's reversible. When it is not, it is irreversible. What is it? The area under the curve. The graph itself is showing you expansions or contractions. If you are going like this, as you are going forward, it's showing you what we call adiabatic expansion. Yes, it's arrow that indicates where it's facing. By the time we get to Carnot cycle, it's arrow that is used to indicate where it's facing. So that's that for that. That's that for that. All right, next. Now, limitation of the ideal gas model. So, molecules are not point masses. They have finite volumes. That's one of the limitations. When you hear the word limitation, some of the things that makes the theoretical entology they present not too acceptable because of things like that. Yes, we call them drawbacks. So intermolecular forces exist, but they believe that intermolecular forces do not exist. But they do exist. Deviations become significant at high pressure or low pressure. Eh? Deviations from an ideal state. Eh? When you increase pressure, you will not notice them again. Free gases be liquefied, and then you watch for mitigation, just in case of recurrence. Now, finally, they cannot explain critical phenomena of phase transition. They only witness it. So causes of deviation from ideality. Causes from ideality. intermolecular equation, finite volume, reduce available urine, and increase pressure more than ideal. We're talking about the effects of deviation from ideality. So this one now is even dominant when you're in a high pressure place. So molecules attract each other. Is there? So they're very high. All right, so the next. So we're looking at the viral equation of state and the Van der Waals equation. The equation is the Van der Waals equation. The equation of state, I believe it will still be presented. So a general equation that accounts for the intermolecular interactions using power series in densities. Using power series in terms of densities. Okay. Van der Waals equation improves an unideal group. So you see, Van der Waals equation basically you utilize it for real gases. For what? Real gases, not ideal gases. So under what condition will the gas start behaving real? When pressure is high and temperature, you understand? The system starts behaving like a real ideal system. Okay. So let's go. Next slide. Critical constants. At the critical point, liquid and vapor phase becomes indistinguishable. Critical temperature, maximum temperature, and all of them become indistinguishable. Yeah, at critical point, does not mean everything is zero. Critical point is the point where a fluid starts becoming like a supercritical fluid. And what was that? What do you think supercritical fluid looks? Your four phases begin to exist. No? Well, three-dimensional beings. Three-dimensional beings. So that's for that. Next. Joule-Thomson effect and liquefaction. Look at what you need here. Some of these things are not necessary for you at all. And then, yes, ma'am. What is it? Yes, that's what you need to grab. This is that place that they call critical points. After which, when you go, you become a supercritical fluid. Normally, I was supposed to show the triple points. I'm supposed to go to triple points. Side. You have a question? What? I'm not hearing you. The face diagram. It's showing you information, more information about, it's showing you more information about the about the property of what you plotted. Yes, now. That one that we just saw now. I've even forgotten what it looks like. But it's actually how they return. This one is for water. Yes, this is for water. You see it, you will know. CO2, you see that place that is in solid, that's it bend forward. Bend, I want bend and enter inside. So, so Carnot cycle, it deals with ideal gas. So good. The Carnot cycle is the ideal cycle that gives the maximum possible efficiency before so so the Carnot cycle is the ideal cycle that gives the maximum possible efficiency between two reservoirs. So we have two Carnot cycles. But I said that Carnot cycle is the ideal cycle that gives the maximum possible efficiency between two standard students who take class today. So, what are the processes? Number one, we have the isothermal expansion, right? That occurs at TH. Now, please follow me. Oh. Look at that TH. When they tell you to draw or explain the Carnot cycle, you let them understand that Carnot cycle is a cycle that gives maximum possible efficiencies between two reservoirs. I get what I'm saying. When you check that, when you check him, you will see that what? You will see that that's not even his problem. He's doing that one inside his house. Now, isothermal expansion at TH, adiabatic expansion at TC, isothermal compression at TC, adiabatic. These are the three things, four things I need. No additional subtraction, no help me bring out rules. No. So, all I want to say is something like this. Like this. You understand? Yes. Okay. What I need now is not this. I need sleep. Sleep I need.